So everyone in the room, it's 9 o'clock already, so I think we'll just go ahead and get started. Our first 3 to 4 presentations this morning are online. We're still waiting to see if the first presentation is going to show up or not. If not, Peter has some things to show. All right, I say we give the guy, or we give the person a few minutes, and then you should take it away, Peter. Okay.
Okay. Well, I can say a couple of things.
Okay.
And just speak of if Frederic shows up. So welcome everyone to the MWG only session. I'm Peter Leutzen. I'm the internal co-chair for the MWG, and we have 2 external co-chairs, Kevin Reed and Uwe Vahn. And unfortunately, none of us are in person this year, but Cecile is there, and she is the MWG science liaison. So we have a pretty exciting list of talks here this morning. We'll start out by speakers from Central European time zone. So we're not sure if Frederic will show up, as you just heard, or then we'll have 2 talks from the NORD-ESM group, who share most of the atmospheric component with CESM. And then this year we got quite a few software talks as well. Many modeling groups are exploring implementations in other languages than Fortran. For example, DOE is using C++ Cocos. There's also a project with Icon to go with that. There are a Python-based approach, for example, JAX. So we'll hear about a version of CLM in JAX Python, and then also there's been efforts to port the spectral element dynamical core to JAX that Owen Hughes is going to talk about. Then we're going to talk a little bit about our quote-unquote legacy software. So Mark Taylor is here from DOE to talk about topography generation for really high-resolution grids, where he's using NCAR's software, or modified versions thereof. Patrick is going to talk about nudging capability in CAM, and then we go into deep learning or machine learning stuff. Then in the afternoon, we're going to have a lot of interesting talks here about tuning. So Rich and Cecile will be back talking, and Vince is going to talk about his quad tune approach, and then other tuning approaches with CAM. So I showed this table here on Monday that shows different versions of CAM in terms of parameterization choices, dynamical cores, model top, number of layers, and what land and ocean model is sending underneath. I hope I spelled out all the acronyms on this plot here. There's a lot of information, but I just want to make a couple of remarks here related to what's in CAM 7 that we didn't get to talk about on Monday. What we didn't get to talk about on Monday was, Ben talked about higher resolution application of CAM, where prognostic momentum fluxes have shown to be really beneficial. We spent the past year attempting to bring down our vigorous hydrological cycle. I believe Rich is going to talk about that. We had a lot of success in AMIP, but a lot of stuff really didn't work out in coupled, unfortunately. And then Adam Harrington talked about this Club MF option that we also hope to release with CESM3 that's used for ultra-high resolution applications. For the radiation package, we also spent the last year making some modifications to it, because it only works up to a little bit lower than 80 kilometers, so we had to make some modifications to make that work. So I've stolen Julio's Backmeister's slide here from the CAM 7 meeting. So on the left-hand side, you see the vertical grid and pressure on the x-axis. When you get up about 1 Pascal, our RTMG doesn't really work anymore, so we kind of just did a kludge so that our model would work with the 80-kilometer tox. We basically just limited our GMGMP up to 1 Pascal, which you can easily do in a pressure-based coordinate. But when we're running with the MPAS dynamical core that uses a height-based vertical coordinate, where pressure is diagnostic, it could pretty easily happen that you get pressures above 1 Pascal. So this solution we had for spectral elements was not really viable with MPAS, or not a general solution. So what Julio suggested was that we transition to the radiation package that's used in WACOM above 80 kilometers. It's called Fomichev radiation for those of you who are aware of that. So we basically merged the two above 55 kilometer-ish. So thereby having a more robust solution to this problem. Speaking of MPAS, I also want to make everybody aware that we have support for MPAS in CSM3, although it's not our default dynamical core for 1 degree applications, but it sure is our default dynamical core for 3 kilometers, since our SE-CSLAM dicore is hydrostatic. So behind the scenes, there's actually been a lot of work going on making MPAS work well with CAM physics. So I highlighted most of it here. So as I alluded to before, MPAS is a Z-based vertical coordinate model. CAM physics is pressure-based. So when you couple the two, you have to make sure that you convert the state in a consistent way. And one thing we care a lot about in CAM is that we have a closed energy budget. So what was done was we made sure that physical dynamic coupling is consistent, and then we also adapted the energy fixer that sits in CAM physics to work with MPAS. So in other words, it will use the height-based version of total energy, where the model top is at constant Z, not constant pressure. So the energy fixer in physics fixes energy consistent with the dynamical core. It also worked, this is a while ago, with Bill Skamrock on selecting advection operators in MPAS. That gave us really good correlation diagnostics. That's something we pay attention to make our I almost call them chemical colleagues happy, or like the chemists happy. Also, as I just mentioned, RTGMP was problematic with MPAS. We fixed that. That approach is used in whatever dynamical core you used with the 80-kilometer top. And then we also implemented sponge layers in CAM physics. So it's just hard-coded damping coefficients for the vertical diffusion, and that's really useful for spinning up MPAS, and it's also been helpful for stabilizing WACOM configurations that are particularly hard to stabilize with less diffusive dynamical cores, such as SE-CSLAM and MPAS. Also, there is work going on at NCAR and with collaborators on a deep atmosphere version of MPAS. So all the other dynamical cores we have right now in CSM have the shallow atmosphere approximation. So once that get in, that will really make a big difference for WACOM-X or geospace modeling configurations that go all the way up to 600 kilometers, where a deep approximation really makes a difference. The other thing where there's been some work going on is our topography software. I haven't mentioned that in previous meetings, but here is an update. With the help of John Truesdale, one of our software engineers here, we made a command line interface for topography generation. So here you see the command that's used to generate the default topography for the spectral element dynamical core. We made sure that this command here is also stored in the metadata when you generate the topography file, so that you can easily regenerate it in the future. A reason we have done that is that we have a lot of files floating around where we have no idea exactly how they were generated, because they were made a long time ago or by people who are no longer at NCAR. So we find this is a really nice feature to have in the topography software. So some options we have adopted by default. We do not smooth topography over ocean points. That's similar to what the MPAS-A group is doing when they generate topography. So I mean, there's no discrepancy between what the different components see when you're over ocean. You have zero elevation over ocean. I did a lot of work together with Mark Taylor on reducing spurious mixing or noise near steep topography with the spectral dynamical core. That was achieved by subtracting reference profiles before you apply hyperviscosity and also in the pressure gradient force. And this meant that we could actually run with much rougher topography than we typically have used for climate simulations without generating excessive noise. So the smoothing scales here, we just chosen to specify them in terms of this number here. So 100 kilometers is just what is traditionally used in climate modeling for a 1 degree model. So if you change it to 50 kilometers, it basically means your topography is twice as rough. We did a lot of simulations trying to switch to that because topography is closer to the truth if you did that, but the circulation unfortunately was somewhat degraded. There were improvements here and there, but overall it was actually degraded, which is I'm not happy about, but that's life. Also, there is a variable in the topography that's called SGH30. That's a variance of topography below approximately the 6 kilometer scale that goes into our drag schemes. In CSM2, we artificially enhanced SGH30 over Greenland. We've also adopted that for CSM3, but we're also applying that over Antarctica. Again, a lot of investigation was done here. If you go look at our CAM7 slides, you'll see a lot of results. So you can go there if you would like to see more details. Basically, we created a mask over Greenland, similarly over Antarctica, and then there's a multiplication factor you can apply to SGH30 there. And here's some plots from Adam Harrington showing precipitation in gigatons per year over Greenland. Below you have the ice snow melt in gigatons per year for different versions of the model. So the control is your yellow line here. The black line here is a regional model considered the truth here called RACMO. You see we're overdoing the precipitation in our control here, but then when we start roughening up SGH30, we kind of move closer to RACMO. So that's the main reason we have moved to this approach also in CSM3. We have different versions regarding our vertical levels. So we have a mid-top model with 93 levels, and then we have a low-top version with 58 levels. They coincide throughout the atmosphere. So the boundary layers are the same in the two configurations, but obviously the 80-kilometer model has levels for a well-resolved stratosphere. We've been running LT a lot during the development because it's cheaper, but we've had very recently discussions here about what should our workhorse be. So in other words, if you refer to the CAM7 model, now what configuration are you actually referring to? And we would like to have the MT be what you're referring to. That would be our workhorse configuration. I'd like to highlight the cost of the model. So we are really, really good at making expensive models. If you look at CAM6 that have 32 levels and a 42-kilometer top, and with that model, we're able to get about 30 years per day. With the new vertical resolution, where we roughly doubled the number of vertical layers, we also roughly doubled the cost of the model. Actually, it's getting a little bit more expensive than double. So we're getting about 12 years per day with the LT. And the SO specified here stands for specified oxidant. So that's the cheapest version you can run the model with, since we are not affecting a bunch of chemical species. Then the mid-top model has 3 times the number of vertical layers, roughly, compared to CAM6. And that one gets about 9 years per day, so it's roughly 30% more expensive than the LT model. The main motivation for doing that was to be more in line with other major models around the world that do have a top up at 80 kilometers. And the benefit of that is that you get a well-resolved stratosphere, and you can thereby get a free-evolving QPO, and your polar vortices are not in the sponge, but you got to pay that price of 30% extra cost. The model with almost the full bells and whistles is the T4S version. So that's called climate chemistry, where we advect around more than, I think it's about 130-ish species. And if you do that, you again double the cost of the model. So it's unfeasible to run all our simulations in that configuration, but we do need to run it to provide forcing data for the MT version of the model. It came up in the discussion yesterday that the model is very expensive. The university community and other users would like a cheaper version of the model. As Ayla mentioned, we do have the CAM-SEMA project where we're making sure that older versions of CAM physics are available. So as you heard on Monday, CAM4 is a whole lot cheaper, is available in the CAM-SEMA framework, and we are working towards getting CAM5 in there as well. But there's also, I think, a need for a CAM7 cheaper version. So obviously you can run the LT version to have a cheaper model version, but there are also other options that we could explore once CSM3 is ready. So one could run a 2-degree, get a roughly 8x speed up. One could run lower resolution physics grids that's available in the Spectrelement DICOR that gets about 20% speed up. There's also been some talk about reducing the number of vertical levels from 58 to somewhere in the 40s, keeping the boundary resolution the same, but change the resolution in the free troposphere. And maybe even one could consider a single position, which in theory can deliver 2x speed ups at best. So I assume Frederic did not show up, but if anybody has comments or questions about CAM7, please speak up.
Can I just shout out my question?
Sure.
Peter, I had a question about the SGH30. You said it's artificially strengthened over certain regions. I was just curious how that's done.
Very, very simply. So in the name list here, you see it as Greenland Antarctic SGH30 factor. So you specify a factor here, and it basically goes in and takes SGH over the mask over Greenland and the mask over Antarctica, and just scales the existing value of SGH30 with, in this case here, 2.5. So it's very, very simplistic.
I should say if people online want to ask questions, they can put them in the chat. Are there any other questions in the room?
Peter, you're talking about like having a capability for university users to run. And I'm wondering, is there any benefit in understanding how cheap is cheap enough for them? Because you could just take the approach that like, we're going to make it as cheap as we possibly can. And yeah, but it would be nice to understand a target for university users, I think. Not that I know what it is.
Yeah, that's a good point. Maybe we should try and figure that out. So yeah, it'll be nice to get to CAM6 or faster levels, but that's a good question.
Yeah, because if it really is a threshold thing that like above this cost, I'm not going to run it, I'm going to run something else, or run something old. But below this cost, I'll contemplate running it. Because it behooves us that people actually run CAM7 to do their science in terms of moving forward.
Yeah, it'll be good to get some data points on that. Totally agree.
I was going to follow up to, I think the key is to understand what the university community is using the model for.
Yeah. Yeah.
You see them wanting a stratosphere resolving version, maybe. Maybe not.
Yeah, I mean, it'll be somewhat bespoke in terms of the pieces that people want rather than just CAM7 at a cost, you know.
Right.
It's a good point.
Yeah, because it is going to be a significant amount of work to put that version together, depending on what we choose to do. Alrighty, it's exactly 9:20. So I'll hand the mic over to Ada Bjarmansen from the NOA-ESM group.
Thank you. I'll just share my screen. Do you see my presentation?
Yes.
Great. Yeah, so my name is Ada Bjarmansen. I work in the coordination team of the NORDESM development. NORDESM stands for the Norwegian Earth System Model. And we are currently in the process of finalizing the NORDESM 3 version for CMIP 7 fast track. And I'll show some highlights, some challenging and some biases we are facing of the model development that's going on right now. And I put some names here, but those contributed directly to the slides. But I just want to emphasize that it's really a team effort and a lot of people contributing to this development. So why this maybe is of interest also to you is that NORDESM is in large part based on CESM. So I tried here to indicate in blue the model components that are CESM based. So we use CAM for atmosphere and CTSM or CLM for land, SICE for the sea ice and Mozart for river. But then we have some differences as well. So that's indicated in yeah.
Your slides are not advancing on our screen.
Oh, that's not good. Okay, I can try again, or let's see. Okay, let's try. Just stop me if it doesn't work. Maybe you have to share. Yeah. Okay. So blue boxes are CESM based components, and then we have the pink boxes which are unique to NORDESM. So we have a different aerosol and chemistry scheme, which is called Oslo Aero. And then we have a different ocean component, the Bergen layer ocean model, and ocean biogeochemistry model connected to that. And then we have some joint development efforts, so the land ice system, and also we run CTSM with FATES, so we have dynamic vegetation, and that effort is led by Rosie Fisher. And I thought also emphasize this, even if it's not like atmosphere, but I think CESM in the future is planning to transition to using FATES as default. And we are currently using FATES to tune the model. So hopefully you can leverage a little bit from what we are doing here. And also the communication and CMAPs and CDEPs are joint developments. Yeah, so we are currently preparing for CMIP 7 fast track. We plan to release 2 versions, a low resolution, which is NE16PG3, so 2 degrees-ish for resolution for atmosphere and land, and then 1 degree for ocean and sea ice. And then 1 medium resolution version, so NE30PG3, and then 1 degree resolution for ocean and sea ice. And the plan was to release it 1st of January this year, but we are not there yet. But we are working really hard, so we try to still try to finalize it and run baseline simulations and the scenarios this over the summer, so to be in time for fast track. And why we plan to have 2 versions is that there is, like Peter just mentioned, there is a push from the community here, and especially the universities, to have a cheap model version. And also the experience from CMIP 6, where we also provided two versions, a low resolution and a medium resolution, was that it was actually the low resolution which was used most for the MIPS and the MIP contributions. Yes. So it's ambitious, but hopefully we'll get there. Yeah, so I just wanted to, since Peter was showing it, that this is the throughput we have. So for the 1 degree version, we approximately 7.5 years per day. And for the 2 degree, it's around 14, 15 years a day. So we ended up doing most of the model development also in the 2 degree or the low resolution version. So just to say which CAM version we are using in our CAM7 NOR. So it's based on a CAM6 for 121 tag. And I know you have had a lot of tags after that, but that's where we kind of stopped. But we have added bug fixes from later tags. The parameterization sequence is the same as in CAM7, and we will use the low top version. And we will run with both NE30 PG3 and NE16 PG3 grids. And then we have modified PUMAs to use the random forest ML secondary I scheme. And then we have the aerosol and chemistry scheme, which is then different from what is used in CESM. So it's called Oslo Aero. The radiation scheme we will use is RRTMG. And then we have several diagnostics fields which differ because we have different aerosol and aerosol module and also output. But I think there are like the bulk part is very similar to this tag. So here is just to show some short time series of the versions. So in blue we show the 1 degree resolution. So this is the couple model. Dashed is the previous generation, so what we used for CMIP 6, and solid is the ongoing development version. And then in orange is the low resolution version. So if we start with the surface air temperature, you see that you see the 1 degree is not fully stable yet, but the 2 degree, which you have done most of the spin up and work on, is quite stable. It's colder than the previous generation. And the 2 degree is also warmer than the 1 degree, but this is what we see across generations. I think it's a quite common feature. The hydrological cycle is much stronger. We have done quite some effort to reduce it, but it's quite it's much stronger in the current version. It's also the same strength in the two model versions. Total cloud cover is larger. Short-wave cloud forcing is less negative. Long-wave cloud forcing is also less in the current version. And then, so this is the fully coupled model. So the AMOC strength is also reduced compared to what we saw in the previous generation. And we don't have this problem with the Labrador freezing over, but Labrador Sea freezing over, but we have a weaker AMOC. But if we look at the differences here, that it's larger differences across model generations than across the resolutions. Yeah, so this is showing the surface air temperature for the 2 degree here and 1 degree here, and the difference. So we see that the 2 degree is warmer and mostly over Northern Hemisphere land. But if we look at, so this is showing the difference from ERA 5. It's maybe not the best comparison since ERA 5 is more present day and has a very strong temperature bias over the Arctic, but still, in general, the model is quite cold, and especially over land. So that's one of the biases we want to address before the release. For PRECIP, again, 2 degree and 1 degree and difference. And the biases, the difference from ERA. So we see that the biases are quite similar across the resolutions. One thing is that we have less precipitation in the 2 degree over the Amazon, and we have challenges with the vegetation dying there due to drought. So that is one thing we also are trying to address now. Yes. Yes, and I have to say one more thing. We have quite extensive precipitation in the Pacific and over the Southern Ocean. So we get a very fresh Pacific and fresh Southern Ocean. And we get a strong, so that creates a strong halocline in the Southern Ocean, as we don't get mixing from water subsurface with the surface water. So we have quite extensive sea ice in the Southern Ocean. And also the seasonal cycle is a bit off. And this is also the same in both model resolutions. If we compare NORDES-M 2, so the previous, what we used in CMIP 6, the previous generation, with NORDES-M 3, which is like the ongoing version, we have, so this is showing the bandpass filtered set 500 surface for winter, spring, summer, and autumn. And we see that we have low storm activity in the new version. So that is also something we want to address before we release. And to address all these biases, we have been running coupled PPEs. So the main biases we are trying to address now is this meridional gradient in temperature, that we have 2 cold high latitudes, and we also have 2 cold land versus ocean. And then we have a too strong hydrological cycle and too much sea ice, both extent and thickness. So what we have done is to run fully coupled with the 2 degree version, pre-industrial, and then we have perturbed parameters in all the components. We have run several of these, but try to restrict ourselves to about 75, 80 members, which we run for 5 years, and then we filter them based on the top of the atmosphere imbalance. We continue approximately 20 members for 15 years, and then again reduce the numbers to 5 members, which seems the most stable, that we can run for longer to get good ENSO diagnostics and such, and also get the ocean needs some time to respond. So for the one PPE we did just before Christmas, we changed or looked at 4 CAM parameters, 3 for the ocean, 5 parameters for land, and 1 for sea ice. And then from that, so this is showing then in blue the first 75 members for 5 years. So we capture quite a large range of behavior in the couple model. And then based off the top of the atmosphere imbalance, we continue the orange ones for 15 years, and then reduced again and continue the green ones for 40 years. So as you can see, that it's quite stable with quite different climate. And none of these versions are the perfect model, but we'll now try to use that to assess the biases we see now. Yeah, and then we make regional regression slopes to see how these parameters impact several variables in the global, and then for different regions, also over land. And then you see the land parameters pop up, and also over the ocean. Yeah, and we have one now because of this sea ice and also the land ocean contrast. We just completed a new coupled PPE with more CAM parameters, but also sea ice parameters to see if that can help us with reducing the sea ice in the Southern Ocean and also the precipitation. Yes, then I just want to very quickly to show you the historical one historical member from the current version. So we just completed this one, and this is the current version of NORDES-M with 2-degree resolution. And this is the NORDSM 2, which was used for CMIP 6. So you see that it's much colder, but it also warm more than what we saw. So if you look at the temperature anomaly, I also included Hadkrut here to compare, so that we better capture the warming compared to NORDSM 2. What we don't, or maybe not so evident, is that we had quite some cooling here, probably related to the aerosol forcing, and that seems a bit weaker in the ongoing version, but that we need to look more into. But for just some variables here, the precipitation is increasing over the historical period. Total cloud cover is decreasing slightly. Shortwave cloud forcing is strengthening a bit. Long-wave cloud forcing is weakening. But the ocean temperature, here you see that it's only warming, while in NORDSM 2, it was quite stable and actually cooled until like 1990s. Then it started to increase again. This behavior we don't see in the ongoing version. And also this is reflected in AMOC. We see this strengthening here before a strong weakening in the 1990s. And I think this is seen across many CMIP 6 models. But in the ongoing version, we just see a weakening. Yes, and this is showing, so this is maybe a better comparison to ERA 5 for the same years, the historical simulation we have been running. And this is the different from the pi control state or baselines simulation. So you see the warming and more warming at high latitudes. And this is the difference from ERA for the same years. We again see this cold down and cold high latitudes. Yes. And then I wanted to end with just Mariana has included, or she had made like a nudging refactor routine that we use now. So before we had to, for nudging winds, for instance, we had to use a separate file for every time interval, and we also had to regrid them to the model grid before we used it. So if we wanted like high time resolution, it was a lot of files that we needed to do nudging. But now everything can be done online. And you don't need like one separate file for each time step. So you can have one file with all the time steps, and then CDEPs will do the regridding both in space to the model grid. So you can use finite volume, for instance, to SE. And also time interpolation will be done. And she has done a lot of validations to see that this is conservatively regridded. So that capability is in NORDSM, and she has also added a routine for regridding the forcing files. So now we can, before all the files from different CMIP scenarios, we had to regrid before it was read by the model, but now this is done online. So that's a really neat capability. And I think you can just, you're using CDEPs, so I think it's just available for you as well. Yes. So we hope then to fine-tune the CMIP 7 versions of NORDSM 3 in the very near future. Also using then the result from these coupled PPs. And we're also trying to streamline the workflow for tuning with the PPs. So it's straightforward for the NORDSM community to use. The code is on GitHub, and also we have adapted the way you also have documenting all the simulations on GitHub. We're trying to do it quite similar way if you're interested. Yeah, and if you have questions or comments, or you can just contact us or ask questions. Yep, that was it.
Yeah, online we can't hear the clapping, but I can see it. Are there any questions in the room? I can see a hand.
Sorry. Yeah, thanks. It was a good talk. I have almost a request, sort of. You mentioned when you were talking about CAM that you guys have a ML emulator of secondary ice formation in Pumice. Has there been any, I assume that's living on some sort of fork. Is there any, I guess it'd be really cool if you all could push that back to mainline Pumice, because I could imagine some folks around here would be interested in that capability.
Yeah, because it currently lives in, like, it's in release Node SM versions, but not, we can push it back, of course.
Yeah, awesome, great, thanks.
Thanks, Ada, this is Dave. I'm curious, when you're doing this like 2 degree and 1 degree stuff, are you bouncing back and forth, or are you just staying in 2 degree and then going to 1 degree once every 6 months, or is there some sort of strategy?
No, we have actually, they are both running in parallel. So we have a 1 degree and a 2 degree version running in parallel all the time.
So every time you're doing a new simulation, you're doing it both in 2 degree and 1 degree, or just?
Yeah. Yes, but we have. So this fall we used mostly the 2 degree, and we also spun up the 2 degree ocean. So the 1 degree has been, we paused it a little bit, a couple of months, but now we're trying to do it in parallel. So now when we are updating the 2 degree, we're also trying to update the 1 degree. We'll have a meeting tomorrow to see if we can find even like better ways of doing this simultaneously and exchange the information. What we find in 2 degree, we can transfer it directly to the 1 degree. But it's the work is happening in parallel, and they are not very different. I mean, they have slightly different C8 values, for instance, to get them balanced, but it's not like a huge difference between the two.
Okay, thank you, Ada. I think we'll move on to Thomas Toniazzo, who's going to talk about local energy conservation in CAM.
Trying to share my screen. Can you? Yes, you have
We can see your screen.
many screens. Yes, and I expect this should go on slideshow mode. How about now? Is this the presentation?
Looks good.
And does it switch side?
Yes.
Okay, brilliant. So thank you very much for having me once again. I'm changing gear totally from the incredible talk I've heard so far, because this is very short on results and very thick on methodology, I'm afraid. It's the result of a few years of work, in fact, in trying to resolve this issue of energy conservation in CAM, which I and Peter have been collaborating for. And it just so happens that while everyone was very busy with CIMIP, I decoupled completely from that and focused on this. So I was able actually to make progress that kept eluding us, and finally crack the nut and find how this energy conservation for the physics of CAM can be done and should be done. So I'm trying to explain it here and show a few preliminary results that I have that are based on very simple setups that are still not what you'd expect to run in a CSM or an RSM for CIMIP or anything like that. So I want to first frame the problem, namely, we know we have a task to do with these models, namely to estimate where all the heat that is coming into the system at the top of the atmosphere is going and what warming it is producing. Climate system is currently absorbing, according to some estimates in the last 15 years, about 400 terawatts of energy. Most of it obviously goes into the ocean. A small fraction of it stays in the atmosphere. We are running a model where, in fact, energy is not conserved, and there is a fixer invoked in order to make it look as if that is that puts the non-conserved, so conserved energy back into the system that is of the same order of magnitude of the signal we are trying to simulate. So this is potentially a big problem, and we should at least understand it, I think. So this energy is put back in an arbitrary fashion. It is the most harmless way, presumably, named as a uniform heating of the entire depth and width of the atmosphere, which procedure, however, does imply forced heat transport. So heat is not conserved locally, and the residual then is carried somewhere else. And this potentially can actually affect not only the simulated surface temperatures, but also the climate sensitivity, because you're doing this before feedbacks, so you are letting the physics respond to heating that is unphysical. And therefore, the model's response can be also unphysical. I'm not saying this is what is happening, but I'm saying this is a possibility and we need to be aware of it. So what's going on? What happens is that we've talked about this before. DME adjust at the end finds atmosphere mass that isn't consistent with the water updates that have happened through the physics cycle. So the dry mass needs to be adjusted. So the state is changed. However, that also changes the enthalpy, the total energy of the state. And that change in total energy that is not physical and doesn't correspond to any associated boundary fluxes is then corrected by the fixer. So the way to adjust to actually repair the model, which I'm saying fixing confusingly, the model is to replace this DME adjust procedure with something that actually conserves energy. There are two possible ways of doing this. I believe there are only two in the primitive equation set. Namely, either to leave all the water consistently massless, including water vapor, or to attach the material heat to the water mass. So water should have a non-zero enthalpy associated to the material, which isn't latent heat, but is sensible heat. Now, option one is not feasible and perhaps not even very desirable, because there are already assumptions elsewhere that obviously water vapor carries mass, carries energy. So we don't want really one. The way forward is two. And one of the crucial steps in order to be able to enforce two is to realize that we need to update the thermodynamic functions of CAM, namely for the water enthalpy. Water exists in several phases. The enthalpy of the different phases need to be consistent. And in order for that to be the case, there need to be defined the reference phase of water, which is already done in CAM. There needs to be explicitly defined a reference temperature of water, which isn't done, and the 0 point enthalpy that also isn't there in CAM yet. These three quantities are crucial in order to make sure that you can conserve energy, because you need to have the right functions in order to be able to do that. That is one of the crucial steps that we haven't realized fully for a long time, I believe. And then you come to point two, where is actually reformulate the adjustment at the end of physics in order to conserve both water and enthalpy. And for this to be possible, there needs to be a realization that the mass adjustment is changing the enthalpy of the state. The pressure adjustment is changing the enthalpy of the state, because the pressure is actually performing work. The material enthalpy of water that is inserted or extracted from the atmosphere carries energy now, so that needs to be accounted for. And finally, the heat capacity of moist air, the CPs that are of the mixture are also changing, and this implies that for a given temperature, the heat also changes. All four terms are crucial in order to be able to satisfy the dynamical equations that were laid out and described in detail in the monster paper of Peter, Nicholas, me, and co-authors, where we actually laid out the problem in great detail. So once this is done, then we have a sum of all these terms, and it turns out that the sum of all these terms looks meaningful, this time, namely, it looks like a heat exchange between the wet mass of the atmosphere and the dry mass of the atmosphere. There is a term that depends on the temperature difference, and there is a term that depends on the geopotential difference. If you are inserting or extracting water from the atmosphere at the local temperature and at the local geopotential, then this term is zero, and you don't need to update anything. However, the boundary fluxes do not come with the temperature of the upper atmosphere or the geopotential of the upper atmosphere, which would be much too much. So they have a specific boundary temperature TB and a surface geopotential Ph. And therefore, there needs to be an energy exchange between water and air in the atmosphere. This energy is assumed in my scheme to happen between the local height and the surface. Right, so now we've got the steps done, we've corrected the thermodynamic function, we've conserved energy, we've exchanged heat necessary. We need to add the material enthalpy flux to the surface fluxes. It's an additional physical flux that enters the energy budget of the system. And we need to make a very important step once we have arrived at this point, namely to make absolutely sure that all the state updates and everything that we calculate is independent of the reference phase, the reference temperature, and the reference 0 point enthalpy of water phases. These are very large numbers, especially H0s is the tens of thousands, T0 is 300. So these are large numbers, and they do change very much. They do change a lot according to the assumptions you want to make on your reference state, water reference state. And therefore, this is a hard test actually to pass, that your results do not depend on what parameters you put into your air composition.f90 file for these quantities. So once this test is passed and I'm happy it's worked, then you need to do the final step, namely finally turn off the fixer for the physics part. That means that now the fixer is invoked with the actual enthalpy of the final state at the very end of T physac, not at the end of the parameterizations, but after the adjustment. Therefore, the fixer is only going to fix the energy imbalance that is due to the dichrome, to changes in the energy produced by the dynamical step. Results look like this. So in standard CAM, you have fixer increments that look like what you see on the left-hand side. They oscillate a lot according to the state and to the fluxes of the atmosphere. From day to day, these are actually daily means. If you look at instantaneous values, they are one more order of magnitude bigger. While on the right-hand side are the fixer increments that are arising from the enthalpy conserving version, physics enthalpy conserving version, which are much more regular, and they are due to the dichrome. So an important characteristic of these fixer increments are that the dichrome gets better as you increase the resolution. So those increments decrease, actually. They're always positive because the dichrome is by nature dissipating energy. And they are reduced if, for instance, you reduce the diffusivity. So I've tried halving the diffusivity, the explicit Nabla operator diffusivity of the sponge layer, and the fixer increments decrease accordingly. While in standard CAM, they actually increase with resolution because the water cycle intensifies, and so the imbalances are larger, and so you get larger and larger error as you get to better and better resolution. So clearly there is a different behavior. It's also important to realize that these global means actually are the result of much larger local tendencies that are of the order of 100 watts per square meter in the column locally. So there is quite a big change in the heat budget of the column locally. And this is documented far better than I'm doing here in the monster paper, Lauritz et al. 2022. Which I would encourage everyone to read. Right. So once we were there, what happens to the radiative response of the atmosphere? I tried a simple test, namely a 4+4K test in aquaplanet configuration, and we do get a difference as expected. It's not very large, but standard CAM has a radiative response that is about 25% larger than modified CAM. And this is what you expect from the artificial heat transport that is happening because of the non-conservation of enthalpy joined with the fixer increments in standard CAM. So standard CAM is actually overestimating the radiative response. That means underestimating climate sensitivity because of energy non-conservation. Not to a huge extent, but still a significant one. It's interesting to note that if I switch off the fixer for standard CAM, so allow the model not to conserve energy, then this radiative response does decrease a little bit. That is, the climate sensitivity does increase a little bit. So it seems that just using the fixer, even with the same local non-conservation of enthalpy, is doing some damage itself, which again is also expected because a uniform increment implies heat transport on a sphere. So I think I'm finding very consistent results from this. And of course, this is just the start of the story, because once we have added this material enthalpy flux to the surface fluxes, we need to pass it on to the surface components, and the CSM or RSM are not ready for that. CSM actually is using MOM, which wants those fluxes. At the moment, they are kind of made up in CSM and corrected with an additional fixer, which is also destroying local energy conservation additionally. So it's not the ideal solution at the moment, but at least MOM can accept these fluxes. So CSM in a way is more ready than RSM to accept these changes. I'm not sure about the land and the other surface components because I haven't looked into them, but I guess there is more work necessary there. For the moment, I have simply tested a slab configuration where I'm heat and water flux correcting the slab in order to maintain equilibrium. And I do see that the climate sensitivity increases by about 10%. With energy conservation, which is a bit less than the 25% we might expect from the radiative response, but that's a pattern effect because the pattern of warming also changes. There is more warming in the tropics, and the warming is also quicker. So this is still a bit preliminary. I need to look better into these simulations, and maybe, I'll do that next. Okay, so I'm ready to conclude. These are my last points. Now, ideally, when we go through the physics parameterization, we would like to conserve enthalpy and mass at each step of the physics cycle. So each process should do that separately. However, at the moment, the time stepping that is done in the physics cycle in CAM is not very good because it is actually producing unphysical intermediate states. And this implies that there are very large cancellation between one step and the next. The classic example is the Mach-Mich cycle, which even fails to converge. So the result, if you try to do that, and I have tried, is that the model crashes. The model just cannot deal with these large changes in state while conserving energy at the moment. So at the moment, it seems all we can do is adjust it at the end. And in order to fix this problem, the parameterizations themselves need to be reformulated with the material enthalpy taken along all the way. A positive side is that net column heating is not affected by this treatment. It turns out that you can do this, and the column heat balance is still fine. The local hydrostatic pressure work is locally accurate, even if you are doing it at the end. So it is not affected by passing through intermediate states. And also that in standard CAN, the errors in the heating that are produced by the energy conservation tend to be stabilizing. They tend to heat too much above and not enough below. While the adjustment error due to bunching everything at the final adjustment together tends to be destabilizing. So there is some hopeful, although of course extremely imperfect, compensation there. Now, there is still a big problem, of course, that CAM-CLUB has an internal inconsistency because of the different equations that the two systems use. So there is a need for an internal club fixer, and which is a column fixer. So that is destroying energy conservation within the column, and this is something that perhaps should be looked at. As a result, for now, the local conservation in the physics that I'm claiming is actually only achieved column-wise and not locally in the column. Final point, which I reiterate, is perhaps I'm having really second thoughts of whether we should use a global energy fixer at all, even if the model is not energy conserving, because I think it's actually potentially adding to the damage, and perhaps it might be better to run it without the fixer and just be honest about it and have a diagnostics online showing the energy non-conservation. Yeah, so this is something that needs to be perhaps thought about. And that's it. Thank you very much for your attention. I'll take any questions.
Thank you, Thomas. Are there questions in the room?
I have a quick question. Thomas, does any of this have to worry about whether the dicor is not hydrostatic or non-hydrostatic, or whether it's on sort of fixed height levels so the volume is conserved, not?
So the thermodynamic functions need to reflect the dicor energy. If the dicor is non-hydrostatic, then you're not conserving enthalpy, you're not conserving hydrostatic energy in this, as I've shown here. You are conserving total energy. So you have CV times T plus the local geopotential. The formulae for the mass adjustment do not change. So the mass enthalpy adjustment maintains the same form, but the CPs have to be replaced with CVs.
Just a quick question here. When you talk about the internal club fixer, you're talking about the energy fixer in the interface layer to club?
Yeah.
Oh, okay.
We have a question from Mark Taylor in the room. There's time.
In EQSM, we're thinking of calling this DME adjust or modified DME adjust after every physics process. And I think you said that doesn't work. Can you explain again why you had problems with that? If I understood your last slide.
Yeah, no, the mass adjustment alone is fine. If you try to conserve energy while adjusting mass, then following the steps that I've outlined, in my tests, I get a crash every time. And the main problem is, in fact, the Mach mix cycle.
Yeah. Thanks.
Okay, thank you, Thomas.
Thank you very much. Thank you.
To move on here, and we can switch gear from hardcore thermodynamics to software and Python and JAX. So, Owen, please take it away.
Okay. Let's see.
Tell me what's going on.
Can you hear me?
Yeah, great.
I can hear you. Yeah.
Okay. Let's see here. Okay, I'll change this window. Can people see my slides?
Yes.
Like in presenter mode?
Yep.
Okay, let me just start a timer. because there's a lot to talk about. Okay, I'm starting off with basically this thing on the left-hand side. I've made a logo for a model that no one has seen before, which comes off as a bit egotistical, but I promise you it's not. I'm the only name here because the software is my work, but it relies on the experience of everyone involved in ChemSE and Home. And on the left, that logo is an alchemical symbol for distillation. What I've done is basically distill ChemSE and Home into a performance scalable version of JAX. I'm about to go sort of deep into math for a little bit. So if that's not your speed, just ask yourself, do I want to be able to run ChemSE on GPU? Well, by the end of the talk, you can. So hang in there. All right. I'm going to start off with 3 scientific problems that sort of motivate this work. Firstly, it's sort of automated model tuning. This optimization problem let you be the less constrained model param, something that maybe doesn't have a direct physical interpretation. And let's say we have some kind of forecast error metric. And then F here is a forecast model. You could basically say, okay, one way to choose parameters is to say minimize over the parameter space, find the one that minimizes my forecast error. And reasonable people disagree on whether this is a great idea, but it's a good idea. It's an interesting idea. And it can be sort of phrased as, what's the optimal choice for parameters that we have more freedom to change? The second problem, variational data assimilation. So the problem is formulated as basically minimize some sort of delta X, which is a model adjustment that reconciles prediction and observation. And in order to do that, you have to calculate the gradient of this cost function, and that ends up being involving this M, which is the adjoint or sort of backwards operator of your forecast model. I'll get into what that is in a minute. So the third scientific problem comes from hybrid physics ML models. So in this, we're doing another minimization problem. Phi or some neural network params, they have any shape, any structure. They basically are K for some very large K. And I have some data set of time sequence observations, a discrepancy function D that says how different are these two states. My sort of forecast operator here, it's a function of both my state at time n and the parameters that go into the neural network. And then this atmospheric state and the next atmospheric state. So basically this is saying, find me the best neural network that adjusts a physical model to fit the ground truth. And F might be some combination of physical subgrid parameterizations and a dynamical core plus some fixer, like neural fixers, that kind of thing. But I've given you 3 problems to show that optimization is a really powerful mathematical way to phrase problems. It shows up everywhere if you know where to look for it. And there's a fact, you really should do optimization using a gradient of your cost function if it's humanly feasible to do so. Like that's what you should almost always do. And so the idea here behind the model I'm showing is I have some atmospheric state at time n, some atmospheric state a couple of steps in the future, and the repeated application of my forecast operator. This would be like one dynamics time step with physics dynamics coupling involved in there. Repeated application of that, and there's this annoying bit of jargon and adjoint that allows you to calculate good search directions for doing a minimization. If you're trying to minimize a cost function of my final state, basically by efficiently calculating the gradient of my cost function at the final state with respect to my initial state. Recall that a gradient is the direction of steepest increase, and if you take the negative, that's the direction of steepest decrease. So basically, an adjoint is a special way to computationally efficiently calculate the best direction to step to try and minimize a cost function. Imagine here that the cost function is just the integral, the difference between your predicted atmospheric state and your actual sort of ground truth observation, like you're doing some kind of hindcast thing. So adjoint, just linearize your model, take the transpose of the typical Jacobian that also gets called the tangent linear model, a lot of jargon here. And then you basically apply it to get good search directions, and you use it for most optimization tasks, more so than the actual tangent linear model. So JAX is a Python library that automatically calculates these differentials for NumPy operations that basically has one code base for CPU, for GPU, and for TPU. If you haven't heard of TPU, they're Google's thing. They're tensor processing units. They are sort of an alternative to GPU, specialized for matrix algebra. But basically, so calculating an adjoint, JAX is a library that takes basically what looks like normal NumPy-based code, subject to a couple of constraints, and gets you the adjoint that I talked about previously. So here we're sort of trying to calculate the gradient of a cost function. And this could be not a scalar function. It could be a multiple like vector output of your function, but then you have to do some extra steps that aren't important here. So that translates into basically jax.grad C, and C here is a Python function that you've done a little bit of extra magic to, and then you evaluate it at your point. So to JAX is important and has shown a lot of promise in terms of merging traditional physical models with ML physics in sort of an ad hoc way. The most well-known example of this is the Neural GCM Google team and a couple of other people. What they did was they implemented the IFS global spectral model in JAX, coupled it to a column-wise deep neural network model, and showed that it produces pretty interesting, physically reasonable results. And it doesn't, it is, one would argue, less prone to hallucinations, because hallucinations that are bad enough will basically crash your dynamical core. And they had to re-implement the dynamical core in JAX in order to calculate that gradient I was talking about as a part of the training process. So Pisces, or the Python Spectral Element Dynamical Cores, is a CPU-GPU automatically differentiable port of CAMACY and HOME. HOME is CAMACY's sister dynamical core with some slight differences and can be extended to non-hydrostatic dynamics. My DICORE isn't non-hydrostatic. I think that's about 12 hours of work to get that done with, but it's public right now. It is at that link there. And it's got a fair amount of source code. The line count isn't a good metric because I'm trying to make things legible, so there's a bunch of white space. But there are extensive unit tests. That's the main thing, is that I've tried to make it so that every function that I write has a unit test, and the unit tests rely on both domain expertise as a dynamical core person myself, as well as just basic software engineering, like if you do something bad, does it crash or does it error in a good way? And right now, it is easy-ish to install. My goal is to make it basically a Python package pip so that you install it in one line, and then you can basically run it. That's a little ways away because the interface is changing. But I'll share a Colab notebook at the end of this presentation, so you can start playing with it today if you want to. Like I said, it's not quite as user-friendly as it needs to be yet, and it's important. It's missing some important functionality that's still not tested well enough to release. So I'm doing Eulerian spectral tracer advection as a first step, just adding a limiter so we can do some tracer consistency tests, but you don't want to run 1,000 tracers with that. And the hurdles to doing like a semi-Lagrangian CSLAM style or islet style thing would take some thinking and would run into some of the hardest places to develop in this code base. So what does the model do right now? Right now, I have support for the CAMACY dry mass coordinate. It can also have variable R-gas thermodynamics, where you treat each dry air species independently. That's a temperature-based thermodynamic variable, as well as the support for the HOME moist mass coordinate. The shallow hydrostatic is working right now. Non-hydrostatic and non-hydrostatic deep are also, the equation sets are in the code base, but the time stepping isn't there to make it practical yet. But the tests are passing on energy conservation. So yeah, that has a Hamiltonian-based thermodynamic variable. I've architected the code so that basically everything that can share a function shares a function. And so there are a bunch of things where there are slight differences between the CAMSE and the way that Home does it, and I've tried to unify them in a way that probably doesn't break things, but it certainly doesn't guarantee bit-for-bit reproducibility. I have support for variable resolution grids, following sort of the tensor hyperviscosity and element local metric that Guba et al., Oksana Guba derived. I think I made a couple of algebra errors in there. Mark Taylor pointed those out to me, and I'm working on fixing those. It has sort of CAM or EAM-like substepping. Basically, you've got Q-split, R-split, E3SM and CESM sort of differ as to those interpretations. So I've tried to use more verbose names so that you understand what's going on, but it's less flexible than the sort of remap substepping that is in the main code base, but it's simpler and easier to test at the moment. There are two methods for parallelism. There's MPI-based parallelism, which violates differentiability for the moment. This might be fixable, but basically, if you want to run JAX or NumPy in like multiple GPU across multiple hosts, you can do that, and JAX compiles Python code, which means it runs faster than standard Python code. And the if you want to try and scale up to multiple nodes, some preliminary tests indicate that that probably works. Multiple host capabilities aren't super well tested, but the test suite should be rich enough to debug a lot of it, unless we run into out-of-memory problems. So the other one, which I implemented on Saturday, is sharding-based parallelism. This is JAX jargon. It is an internal way of sharding, basically splitting up a array across multiple devices, such that from the user perspective and from the compiler's perspective, it looks like a unified array. So pretty different from MPI, but it is differentiable. And I figured out a way to expose basically the same information that MPI uses to be communication efficient to the compiler. I don't know if it's taking advantage of that information yet, but we should be able to fix that if it's not. This JAX is advertised to have multiple host capabilities when you use sharding-based parallelism, but the takeaway at the end of this slide is, do you want to run CAMSE on, say, 20 GPUs split across 5 different nodes? MPI-wise, that should be pretty doable. With pretty good parallel scaling, strong scaling based on a couple of preliminary tests I've done. The JAX sharding, it should scale well up to 1 node. So 4 GPUs on 1 node. If you want to do differentiable stuff, start doing data assimilation machine learning. I think we're a couple of days away from basically having that capability. But going to multiple hosts, it is a younger feature of JAX, so I'm not quite sure how well it works, and also I don't know how well it's been tested on very large systems. So MPI probably going to work, but if you need the automatic differentiation, we're going to need to do the sharding based. These are pretty easy to configure between one or the other, and almost all of the code is shared identically except for one function between MPI-based and JAX sharding. So the design priorities so far have been the model should be versatile and also still have value if JAX becomes unmaintained. Right now, JAX is pretty tied into the Google machine learning ecosystem, and it's unlikely that it would go away anytime soon because there are a lot of stakeholders sort of involved with particularly the compiler underneath it. But the code is designed so that JAX and NumPy expose an almost identical interface, assuming you do a couple of extra programming steps. JAX is pure functional or very close to it, and that changes how you write code a little bit. But if you write code in that way, then the same code runs in NumPy and JAX, same function, same everything. For example, if you change parallelism styles, the actual interface of functions doesn't change at all. You don't pass in extra parameters. It's just entirely internal. So, second priority, the model should be able to run easily and scale to a modest number of processors, which means this isn't really a replacement for CAMSE or Home, particularly Home XX. I've heard a number of times, like a number of people talking about the difficulty of getting CAM in particular, but E3SM, Home, EAM2, actually getting these running on a new machine. I've never gotten E3SM running on a non-supported machine, and I've tried. I would like this to, even if it scales less well to really large numbers of processes, it should be easy to use and also easy to modify. Untested code is unfinished code. If you don't have tests, even if it's just a couple of tests saying, does this work without crashing for reasonable inputs, that really helps. And I've refactored the code 3 times in the last month, so much faster than I would have in traditional Earth system model code base. People keep figuring out how to compile NumPy style array operations so they run reasonably fast in Python. Numba, QPy, JAX, at this point, TensorFlow as well. The syntax, if you haven't written it, is very similar to like Fortran style arrays with a couple of modifications. And as a result, if you write in that sort of lingua franca, you write your code reasonably well, then I'm pretty sure that it's still there's going to be a way to make it fast in 5 years and still run it on whatever accelerator is fashionable at the time. So, some conclusions. The model works reasonably well, with a couple of asterisks. A bunch of things are broken, but the hard bits seem to be correct. All of the hyperviscosity unit tests I wrote are passing. The time stepping for hyperviscosity is a little bit messed up and causes the model to crash sometimes, not because the operators are wrong, but because the time step is wrong. I'm working on that. But shown here is the topographic baroclinic wave case. It is very good at crashing models that are not tuned properly. I know that because I made the test case and wrote a paper on it, and I use it for that purpose a lot. This is a pretty major milestone, and you can see here that I'm actually using it on a refined grid. Don't use this grid in practice. It's just kind of a rough grid, but it does have grid distortion, and things seem to be damped pretty well and consistently with how Home would do it. And then, as of yesterday, I put together a Colab notebook. That's like an online Jupyter notebook where you can run something that looks like Held Suarez. I implemented it over like the duration of eating a donut on Saturday. So I haven't tested whether it's like the Held Suarez is correct, but it looks like Held Suarez. This Colab notebook, you scan this QR code, shows you sort of how the workflow looks for running a model right now. Yeah. So, some conclusions. If you're interested in any one of the 3 problems I mentioned at the start of this talk, the model should be quite useful once I get tracer advection tested and running. I've also only partially tested that the automatic gradients do what they're advertised to do in a distributed memory context. Working on one GPU, things seem to be going well. CAM-SE now runs on GPUs if you want it to. You can't couple the physics, but maybe we could get there. If you want to start porting an intermediate complexity CAM configuration to Python, It'll run on GPU, plus it'll be differentiable. And this stuff works up really fast. Like programming is really quick in this. So yeah, to conclude, I really want to make this a community model. Right now, things are going to break. Things are broken. You're going to use it in ways that I couldn't have imagined. If you think the model will be useful to you, please try using it and open an issue on the repo here. Just in conclusion, I really want to explore if this can be a community model. I know particularly among the sort of younger generation of Earth system modelers, people are pretty excited about this. And I would like to, I've written it up to this point because that's how it works. It was like a side project I did to psychologically cope with feeling like the world was falling apart. But I'd like to bring other people in and see if it can be useful to people. If you fall into one of the following 3 groups, please consider filling out the Google form on the left. If you want to be updated when the model hits v1.0, if you want to provide input on where I should take the model next, implementing non-hydrostatic capabilities, Samuel-Lagrangian tracer advection, finite volume physics grid, disk history files, what should I do next? Also, if you think this might be useful to you and want to schedule a quick 30-minute meeting to talk about an idea and figure out what that might need, also fill that out. And if you know someone who also might like to use this model, these slides will be on my website, owenhughes.org, and just send it to them. So, in closing, some appreciation and gratitude. I wrote and designed this code base basically entirely myself. I got some very helpful, life-saving suggestions from Doma Kimpura at NCAR on the code side. In terms of the math, Drs. Oksana Guba and Mark Taylor are really have helped me a lot in the process of understanding how home works. Peter Lauritsen at NCAR, also a doctor, has helped me get up to speed on how, why particularly CAM is the way it is, how physics coupling should work, starting on that, and also my advisor, Christiana Jablonowski, who's still helping me find my niche in the atmospheric modeling role. So, questions? Did I miss something?
Alrighty, thanks, Owen. So we're running a bit behind schedule. There's a very quick question in the room.
Oh, we have 2. Jesse raised his hand first.
All right. Yeah, thanks, Owen. Great talk. I'm just curious about how did you start the process? Like when you opened the first Python file, did you just like take the equations like that you knew of in the literature and just coded it from scratch? Did you try to translate the Fortran code, the current SE code to Python? Yeah. How did you get the ball rolling?
Good question. Okay, so how I started this project is not how you should start this project. If this question is about how do I start playing around with this or try to start playing around with porting things to JAX, a good workflow and one that I've done in the mature stage of this project is basically go line by line and do a translation of Fortran to Python just line by line with for loops. Runs horribly slow. You have to translate 0 indexing or 1 indexing to 0 indexing, but it works. And then write tests for that really naive function. Make sure that they're all passing, and then make it fast. Make another version that's in the main code base that makes it fast. That has almost always worked. And basically at this point, I can usually turn 200 or 300 lines of Fortran into about 100 lines of Python in, 3-4 hours.
Cool. Great. Thanks.
Yeah.
Okay, we're 8 minutes behind schedule here, so I think we need to move on. But if you can email Owen directly, whoever has the other question in the room, please do so. And let's transition to Aya, who's also going to talk about the Jaxifying code.
Yes. Hi, everyone. I will share my screen. Okay. Everybody should be able to see my presentation. Let me know if there's any issues with the sound or the presentation at any point. but thank you for having me today. My name is Aya Lalu. I am a PhD student in Pierre Gentine's lab at Columbia University. I've met some of you in the past year, and if not, happy to talk to you today and discuss a little bit of the work that I've been doing this year. So with Pierre, we had this idea, very similar to Owen, to start thinking about translating legacy ESMs into JAX for all sorts of benefits. And so in this presentation, I'll show some of the pipeline that we came up with and the steps of how to do this translation in a way that is generalizable and maybe a little bit faster with slightly less headaches for people who are interested. So the main motivation here is really the technical depth that is carried in some ERTISTA models. Specifically, there are many architecture challenges, complex nested hierarchies, and also extensive module level global state with hidden dependencies. There's also the issue of machine learning integration with a lot of bottlenecks in trying to have PyTorch or say another machine learning platform work with Fortran, as well as memory management conflicts. And so, for example, static allocation versus dynamic tensors, or let's say in a specific machine learning problem, like we need a lot more memory or history to answer a specific context. And so that was my initial motivation to try and dig into translating something into JAX. But with that also comes the potential of differentiability. And I won't talk too much about it, given the audience and the talk before, but this was essentially the motivation. So we came up with this pipeline here, and I'll try to walk you through each step. Essentially, we've got a first step that is called a static analysis of the Fortran code. So in this first step, we are looking to look into the Fortran code base and understand the dependencies that exist, all the subroutines within each module, as well as potentially decomposing a specific module into translation units, and even bigger subroutines into smaller translation units. So here we're basically just gathering metadata to better inform our translation steps in the future and understand like how can we go about translating a full code base from Fortran into JAX. What do we do first? What do we do next? And how can we automate it and also make sure that we set ourselves for not like a broken code or hallucinations in our translations. So that's the first step. The second step, I'll be talking about the base agent later on, but essentially that's just what would run the translation for each module at a time, orchestrating between all the different steps that we'll see forward. And so once we have the static analysis that we run once on the full code base, we're looking into the translation agent next, which takes in as an input the dependency graph and the translation units. So the static analysis of the Fortran code base to have an added context. And so from there, we get the Python translation. I'll go a lot deeper into each of these steps later on, but just to show the pipeline, after we have the Python translation, we're thinking of feeding it to a testing agent, which would get us a Python test suite in the case where we do not have already unit tests generated for the specific modules that we have. And then once we have the generated PyTest suite, we can run the tests and then look at the test logs. If they pass, then perfect. We're done translating that specific module. If they do fail, however, then we have a repair agent that comes in place and takes as input the test logs as well as the Python translation, and then the Fortran code that is corresponding to that Python translation that is failing. And so this is an iterative process that I'll go through later, but the repair agent can then, using that input, fix the Python translation, run the tests again. If they do fail again, it can be like an iterative process until like a maximum of numbers that we can set. So this is essentially the pipeline. I'll talk more now about the static analysis that we came up with. So we came up with a custom framework for the static analysis. It's available on my GitHub called Fortran Analyzer. It essentially just uses the libraries FParse and networks, and it is able to adapt to different Fortran code bases to parse it and then get a dependency analysis. So we get a module dependency graph, as well as we can detect any circular dependencies. And then we have a translation unit decomposition, which I'll go in a little more later. Here, this breaks large procedures into smaller chunks for the translation. And then we can, this framework also just generates some information about the code base that we have and understanding the dependencies and visualizing it as well. So these are the main outputs of the static analysis, just the module dependency, which has the information about what are the dependencies of this module, and also what kind of subroutines exist within that module, what kind of variables exist within that module. And the second one is within each module, each unit ID or like chunk that we divided in. And so let me talk a little bit more about decomposing translation units. So there is a specific context limit into LLM calls into to translate. And even though that context window is very high right now, we want to be able to limit it a little bit. So papers have shown that the smaller the chunks that we translate at a time, the higher the accuracy will be from this figure on the top right. And so we are able to truncate these modules into different translation units, depending on like the length of a subroutine. If a subroutine is very short, then the full subroutine is translated as one translation unit. If it is very long, then there is a way to further divide it into smaller units, specifically for nested loops, can be then separated into different units. And so the way that this fits together is then we have a specific units to translate, and we also have an order to them so that the base agent can go and do the translation automatically, one chunk at a time, so that we're able to validate and keep the LLM errors of translation very low. So the second part of why we are using the dependency output is to look at the topological sorting of all of these functions. Essentially, if we translate something in the wrong order, it is likely that the code will reference undefined types, and the LLM then will have to guess the structure of a specific class or function or so on. And so that increases the hallucination risk. And so to avoid that, we introduced something called topological sorting, which has been used in like the papers referenced in this slide. And this essentially makes sure that dependencies are always translated first so that there is no undefined references, and that also the context accumulates with later translation units. And this essentially reduces the LLM errors by 30%, which is really helpful. And so this is what it would look like. This is the order. We would start translating with the the module with the least amount of dependencies, and then work our way outside and then bottom up. And so this is all given in the context of the base agent. So we are feeding the translation units one at a time in that specific order. And for one specific module, we have an iterative translation process. So we translate each unit independently. And then after all units have been translated, we have a second step, which here just does a module assembly. So looking at all the translation units, it assembles them into a cohesive Python module removes any duplicate imports or anything that might cause issues later. And so I just added like a small example here. So this is a module that I had translated, soil temperature mod from the CLM, and it was separated into 8 translation units. So we had 8 unit translation calls plus 1 assembly call at the end. So we called like the large language model API 9 times, and it cost 56 cents to translate that specific module. And so the time that it would take like a person to translate really does not compare to the cost of these API calls. So next is the testing agent, and here we're using the testing agent when legacy unit tests aren't available. So it is able to build a full test suite for the future development and can be used later. And the requirements that we're giving to this test agent is essentially typical operating conditions, but also edge cases, for example, frozen, dry, saturated, boundary conditions, and physical constraints. This is like some of the code that from the testing agent. And so first it will look at the signature analysis from the Python code, then generate test data itself, and then create the PyTest file. So once we have that PyTest suite, we're able to run the tests. And using those test logs and the Python code, if the tests fail, which it is very likely that it does, about 45 to 73% of first pass translations succeed at the first time. So we have 25 to 55% that still need repair. So we're able to give the test logs, the Python code, and the Fortran code to generate a fix. And here we also do it in an iterative process. So after we generate a first fix, we're able to validate the fix by running the PyTest suite again. And if the results pass, then we can leave. If the results don't pass, we can do another pass of the repair process. And from similar studies, it shows that after like 2 or 3 iterations, the success rate of the translation is 80 to 92% compared to 45 to 73%. So that's really helpful. And now I wanted to talk more about prompt engineering and just generally these agents. So sorry if I like skipped a little forward early on, but essentially some of the lessons that I've learned while trying to set up this pipeline is how important a very specific prompt is in the results that like you do get at the end. So effective prompts actually have been shown to have 3 times better results. And how we can make these prompts effective is really by augmenting them with context. And that's the whole motivation behind the static analysis that we do at first. So this is an example of the prompt structure for the translation. So it is able to get the specific file that we want to translate, and then the specific lines that we want to translate. So essentially the translation unit. And then it's able to get the Fortran code, but also the dependencies. So knowing like the specific modules, what are its dependencies, and what are its subroutines, what to expect for the next couple steps of the pipeline. And it also will show the previous translation units that have been translated, and yeah, if there are any, these are some metrics that I had added, which are like complexity scoring or known challenges. But if there are any other beneficial like contexts to add, this is like where it would happen. And then we're able to give like very detailed translation requirements. Specifically here, like I'm asking to use JAX instead of NumPy, or to replace do loops with JAX NumPy operations, or JAX LX scan for differentiability. And if there are any specific issues that you know about your code, you're able to also say it in the prompt. For example, knowing that like we need to be careful with the indexing. Fortran is 1 index space and Python is 0 index space, etc. So yeah, and for each step of the pipeline, we're able to give different requirements that can be like as detailed as possible. For example, here we have some of the requirements for the assembly. So we have like one, combine all units into a single cohesive module, add imports, organize them in a very specific way, ensure consistency across the units, include all the parameters, and add docstring, etc. And more about JAX. So yeah, I was able to add them in the prompt, and that has really been beneficial with the translation. And so I had a first example of translating like one module of club, specifically like the mixing length, and I was able to get it to run and be differentiable. And so these are like just some of the outputs from there. So all loops had to be converted to a specific LAX loop, which is one of like JAX's sister like libraries for differentiability. Yeah. And then I specifically try to use the CLM multi-layer canopy model as like a first proof of concept of this pipeline, specifically because it was a prime candidate for GPU acceleration, given that it was about like 10 times or 5 to 10 times vertical resolution increase compared to the big leaf model. And we also had validation data available for it, I could run it. And so this is the GitHub of my specific translation. I can share this one instead. And so if we go to the source code, we're able to look at what the translation here looks like. So if we go to, let's say, this tridiagonal system solver, we have extensive docstring that is like all generated using the using Claude or using the large language model that you use. We also have references to the lines of like what exactly was translated here, and also within the functions, we have like more line references and more comments that are all like generated automatically from the large language model. We also have the PyTest suite that was generated. So it looks something like this. So we first have like the data that we use, and then also trying out specific functions. So yeah, I also have like some more information about like the prompts that were used here. So these are the Python scripts for the prompts, for the agents. Here are some of the prompts that were used, if anybody would like to look at it. This is very much a work in progress, but some of the preliminary results that I had while trying to run the full JAX version of the CLM are as follow. So some of the variables are still not there yet. I'm still encountering some bugs, but a lot of the variables have a very low mean relative error. such as these. And yeah, for the next steps of this project, I still have some more validation to do, fixing some of those bugs, doing some inline testing and so on. But I just wanted to maybe discuss more with all of you, if anybody is interested in this project or in this question, how we can improve this pipeline and how we can be thinking about translating code bases from Fortran to JAX. Specifically, thinking like for the future, it would be great to have more inputs and outputs from Fortran runs as ground truth to be able to guide the validation at each step automatically, and alleviate some of the validation at the end. So yeah, I'll leave you with some of these takeaways, and please let me know if there are any questions.
Cool. Thank you, Aya. So again, we're still behind schedule, so we have two hopefully quick questions online. So Sam, do you want to start?
Yeah, this is really impressive. I'm a CLM developer, and so I love seeing this kind of work. In my work with LLMs, one of the most, let's say, interesting things is when it runs into a bug in the code that I wrote, and just watching it try to handle that. So have you encountered anything like that during this work?
So I've been able to see like LLMs kind of like struggle with bugs with this specific pipeline. Once I like run it for the workflow, I'm not able to see the logs immediately. And instead, like I wait until like I see maybe like test logs if it does run into an issue then. So I guess like that's just like one issue. Like if like you want to do it automatically with this pipeline, you won't be able to see like what your model does immediately unless like there are specific stops. So for example, if like at the repair agent part, if we are past like a number of iterations, then we can stop and see what's going on there. But before then, it's pretty automatic and goes through the translation testing and repair.
Yeah, makes sense. Thanks.
Mm-hmm.
Okay, Owen.
Yeah, something I found in my port is for me, it's been a great opportunity to a lot of the time code ends up there's important context for the code that's only in a paper, not in the code. And I've found that translating oftentimes is very helpful to like actually bring that context in and improve the quality of the code. Do you feel that there's an opportunity cost in terms of doing this automatic translation, knowing that translation tends to be a lossy process?
Yeah, definitely. I think in my specific use case, I knew that Claude, like the LLM that I had already access to the documentation that's online about the CLM. So it really, I think, like depends on the application. If there's like enough documentation online and not like in most recent papers, then that wouldn't be as much of an issue there. If it is like in recent ones, I think there is definitely like an opportunity cost there, and I think it can always be added to the context if it's something that like we have foresight on. We can ask or add it to the context to handle specific physics or specific bugs like in a way according to like this paper.
Okay, thank you, Aya. We really need to move on here, so we'll switch to C++ with Ren. So take it away.
Yeah, hi, I'm Ren. I'm a relatively new postdoc here at NCAR. And today I'm talking about utilizing CAM Fortran physics in the E3SM atmospheric model in C++. And I know we're a little behind schedule, so I'll try not to bleed too far into the break. So a lot of the motivation behind this work is that there are a lot of ongoing and past projects that involve fixing like sort of this code modernization problem that we have. And so some of the notable ones are CCPP, which aims to provide interoperable physics written in Fortran. We've also had Earthworks, which is a GPU enablement project using OpenACC directives. We also have StormSpeed, which integrates performance portable Cocos and C++ for the dynamical core. And then as we've just recently heard, there's a lot of experimentation with JAX. And so these different code modernization efforts have different goals associated with them. And so sort of the main ones are complexity containment or modularization, right? Physics, package portability, and GPU enablement, which is, a very hot topic these days. And so sort of some things that we're noticing in this like trend of high performance computing is there's a lot more industry support for Python and C++, and support for Fortran, especially Fortran on GPUs is a little bit shaky, and some people think that it's going to get phased out. And then we also have sort of this trend of current grad students and postdocs are mostly being trained in Python or modern languages. And so it's harder to spin up new scientists into these older code bases. And so this project is sort of exploring this idea of how does multi-language support impact community contributions. And so we've seen an example of this with StormSpeed, right, which uses that C++ dynamical core inside of a Fortran application for CAM. And then this project is focusing on pulling in Fortran physics into a Cocos C++ application in E3SM. And so E3SM is the DOE's Earth System model. It's kind of this nice framework that integrates all these different components for you. And sort of the main goal is to provide a framework capable of exascale simulations. It also has support for provenance and like software performance checking, data management, diagnostics, et cetera. And so we're going to be focusing on the atmospheric model, which in this case is EMEXX. And EMEXX has a really nice feature built into it in the sense that it supports language interoperability for parameterizations in physics. It is also provides hardware portability and performance on GPUs, which is really nice. And so they have a pretty familiar interface when we're working with this. So they use the standard XML change functionality that many other models use. And so we can use this, right, to select our component set and grid, set up our compilers, machine environment, batch job parameters, and et cetera, and decide on runtime, time stepping, all of that jazz. And then they also provide an additional functionality provided by this ATM change, which allows us to change atmospheric process settings, not directly at runtime, but we don't have to write a new driver if we want to add in a new process. And so this is sort of analogous to CCPP, which is used by CAM-SEMA, except in that case, you have to define your full atmospheric process in an XML file in advance. Whereas when I set up my compile and job submission script with EMEXX, I can just say, hey, this is what I want this process to look like, and I don't have to touch anything else. And so that workflow sort of looks like we have a configuration script. It goes through ATM change. We now develop our runtime configuration, and then that gets compiled into our source code and run. And so if I want to change my atmospheric processes in order to do this one with Shock B3 and MAM4, for the record, I don't have any domain knowledge effectively, so I don't know if this is even reasonable, but this is what that would look like. I can change it sort of on the fly, and we get our runtime configuration. If I want to change it, I simply have to change it with ATM change. I can also set defaults, but it's nice to be able to sort of swap things out as I want to. And so we can also use this functionality to change log file settings. So if I'm trying to debug, I can change that here. I can change topography files, initial conditions, et cetera. And so EMEXX also provides a lot of very handy like automation and sanity check built into it. And so it handles grid management and time stepping for you. It also provides a bunch of default pre and post condition checks for every time I'm looping through my run functions. And you can add your own. So it will immediately tell you if you have a NaN or something's out of bounds. And this is really convenient because it allows people like me who know effectively nothing about the atmosphere to be able to sort of ensure that, right, I'm not getting numbers that are outside of the realm of feasible possibility. And then it also just handles your data for you in terms of file IO and then field management between atmospheric processes. And so when we add a new parameterization interface to EMXX, at minimum, we really only need these 5 different functions. And so we want to provide a constructor. It doesn't have to have anything in it. We need a set grids function, which we tell it what fields we want and what grid layout they operate on. We have initialize. That's where we can put those pre and post condition checks or initialize anything else we need to. Our run function does all the physics that we want to do. And then we have a finalize, which again can be empty or whatever the user needs. And so to sort of explore how this works in practice, we're just using a very simple identity transform parameterization that I was told to name after myself. But we're basically taking a pressure and temperature field, multiplying by 2, divide by 2, pass it back. So functionally no change to what's happening in the atmosphere here. And then EMXX offers this like bridgeability to different codes or different code languages. So we've also made this identity parameterization in different language bridges. And so in Orange, we have a C++ or Cocos version of it. And then in green, we have the Python bridge version. And then in blue, we have the Fortran bridge version. And we have 2 different Fortran versions that I'll talk about in a minute. But a few things to note about these interface bridges. So for C++ and Fortran, they have different data layouts, as I'm sure many of you are aware of. And so we do have to do a transpose on fields before and after going to Fortran code. And so typically we'll just house those sort of in a struct just to make management easier around that. We did also successfully get OpenACC Fortran to compile with this. So that's really nice because that means we can do everything on the GPU instead of having to do the C++ on a GPU and then transfer to CPU and back. So that's super convenient. And then the really, really nice thing is that we can actually bridge directly into existing code from other repositories. So we can bridge directly to Cub or Pumas, for example. And so this is a little bit chaotic, but this is just a very like brief overview of sort of what this like Python bridge, for example, would look like. So again, in orange, we have our C++, and then Python is, or the green is either Python or the bridged Python. And so we set up our grids that looks exactly the same as if we didn't have Python. And then we have an initialization function, which we then check to make sure we have Python. And then we just call our Python function. And in this case, it doesn't really do anything. And then the same thing happens for the run function where we get our Python versions of the fields and then we pass them to Python. And everything is pretty straightforward with that. And so identity transforms aren't like the most exciting thing in the world. And so we're currently working on doing a Kessler version of this Kessler parameterization in EMXX. And so the Fortran for Kessler and CAM-SEMA is around 783 lines of code, including the meta just for the parameterization itself. And then we would pass that through CCPP to generate code. And that's sort of on the order of magnitude of a couple thousand lines of code. And then for our EMXX bridge, right, we're not using any of the CCPP generated code, just that top parameterization. And so I have added so far about 1,200 lines of C++ code, including a lot of debugging code and a lot of comments and white space. And then I also added like about 180 lines of Fortran bridge code. And so far time I've personally spent on this, it took about 2 months to write all of the different Stengel parameterizations, which was a lot of me just trying to understand what was going on. And then it's been about a month and a half for adding the Kessler code. And it's currently functional. in the sense that it runs to the end and it doesn't explode. But I'm not a domain expert by any means at all. And so a lot of what we're doing now is checking the math and making sure like, I didn't create a variable that doesn't make any sense. But so that part of it, I think, would decrease a lot by working with people who actually understand how the atmosphere works. And so our next steps currently involve verifying Kessler bridge to EMXX versus F Kessler and CAM SEMA or like storm speed. We'd also eventually like to pull more CAM physics into EMXX, and so Club and Pumas are kind of on the list for that. I also have a lot of interest in exploring like additional language bridge functionality. So we've already shown that it works with Python. Doing JAX should be essentially the same thing. And then perhaps having like a Rust or Julia interface, I think would be very useful. We're also looking into automating bridge code generation. And then from a performance side, we would like to compare the memory footprint of running Kessler and EMXX versus just traditional F Kessler approaches. And then it's sort of on the to-do list is also GPU enabling Kessler using OpenACC. And so with that, I would like to thank some of the E3SM developers who have been helping us a lot, especially in the last week, Luca and Mark. And then I do have a GitHub branch that contains all of these like example parameterizations that you're welcome to take a look at. And they do have README files, so hopefully they're relatively easy to follow. And then feel free to reach out if you have questions, comments, or concerns. And I think with that, I'm done.
And are there any questions in the room?
Mark and Jesse?
You mentioned that you had the OpenACC compiling with the Cocos code. Have you actually run that?
Yeah.
And they can both use the GPU at the same time?
Yeah, we, Jen mostly figured out how to get that to work, but it has worked for the identity transform.
Yeah, good talk. It was. I'm just curious. Is this the features that you talked about? Is that like obviously use the whole of EMXX, but could one also use? And I might have my terminology wrong, like the field manager part of EMXX, or do you kind of need the whole model?
That's actually a good question that I don't totally know the answer to.
No worries. Yeah.
I feel like I would be inclined to guess that you probably can, but I don't know.
Okay, cool. Yeah. Thanks.
Alrighty. I think we're ready to take a break here. Is the room okay with a 23-minute break instead of 30 minutes? Looks like it. Okay. So we'll be back at 11:30. And Ren, there was a comment in the chat for you here from Walter Hanna saying I'm a domain expert and it took me over 2 months to make a bridge between the Fortran ZM and EAMXS, so I don't think domain expertise really helps with that process.
It's a green light on.
We'll probably get started. Can you hear us, Peter?
Yeah. Alrighty, let's get back to Fortran. Now Mark is going to talk about topography generation for very high resolution grids. So take it away, Mark.
Thank you, Peter. This is work I've been doing with Walter Hanna, Jishi Zhang, Vijay Mahadevan in the labs. And it's based on some conversations and key ideas from Peter Luritzen and Julio Bachmeister. So just to review, here's a slide from Peter's 2015 paper on the NCAR Topo version 1 tool chain, generating topography for the atmosphere grids, as well as these roughness fields, SGH and SGH30. A key feature of this is it starts with this USGS 30-second or 1 kilometer global data set. Maps that with the binning algorithm to a 3 kilometer cube sphere grid. And then all the future work is done based on that 3 kilometer source grid to get the roughness fields and topography. So one problem with this is that if your grid is finer than 3 kilometers, you have to get rid of this intermediate step somehow. But the intermediate step also plays a key role in the scale separation for the roughness parameterizations. Our work addressing this was motivated by what I call this extreme regionally refined model that was put together by Zhixi Zhang. So this is a grid, global 100-kilometer grid with refinement over the Bay Area down to 100 meters. So it's a many thousands times refinement. The grid is shown on the left, and on the right is a grid colored by resolution on a log scale. So you can see the blue is 10 to the 2, 100-kilometer resolution in this teeny region at 100-meter resolution. And so to run, Zhixi wanted topography suitable for a 100-meter resolution grid and started working with the topography tool chain to get that. She developed or put together using the USGS 7.5 second or 250 meter data set, a global grid to replace the global source grid. And then ran into a bunch of problems with bin to cube. The main one being the amount of memory it needs to process this grid was about over 600 gigabytes. So didn't have a machine that could run that. She was able to run a 500 meter, run the bin to cube code. That's the code that maps to the cube sphere grid, 500 meter data set, mapping to an 800 meter cube sphere grid, but the runtime was over a week. And then we also tried to use some parallel mapping tools to replace bin to cube, but they had a lot of trouble with the 250 meter global grid. There's millions of teeny cells near the poles that they don't like. And then cube to target, it's based on this incremental remap or AAV style algorithm to map the cube sphere to the model grid. So if you update the cube sphere to pretty high resolution, 800 meters, this is an incredibly expensive algorithm. And the Fortran code cube to target that Peter wrote is serial and would also probably take many weeks to run at those resolutions. But she did generate topography from this 800 meter cube sphere grid. And here's a close up zooming in over the Bay Area in this region where the grid is 100 meter resolution. And because the source topography is 800 meter resolution, the result is the topography on the model grid is very blocky. In this picture here, you see the big blocks are the topography from the 800 meter grid, and the smaller blocks that you see the jagged edges is the model grid. So on the model grid, this looks like a bunch of square, perfectly square mountains with sharp corners, and it created a lot of, a stability problem. The model would always blow up at the corners of these mountains unless you reduce the time step by about a factor of 2.5. So this is a motivation for getting higher resolution topography. So what we did is we wanted to replace the binning and the area averaging algorithms used in cube to target and bin to cube and cube to target with the algorithm we call disk averaging, and I'll have a slide on that in a minute. That algorithm was chosen because it's super efficient. We implemented this mapping algorithm in the Moab grid tool package. I'll refer to it as MBDA, stands for Moab Disk Averaging. It is amazingly fast as a remapper, can remap a global 250 meter lat-long grid to any feasible atmosphere grid that we could run in just a few minutes on a single CPU node. And then the surface in this modified tool chain, the surface roughness calculations need some work too. we've redone the calculations so they can be done in terms of mapping algorithms and then NCO operators, NCAP2. So all the algebra is done with NCAP2. And then there's some complications with SGH and SGH30. SGH is the variance between the source grid and the 3 kilometer grid. But if your model resolution has regions finer than 3 kilometers, you want this field to be 0. So we did some work on that. And the similar issue with SGH30, that's the variance between the 3 kilometer grid and the target grid. And again, if your target grid is finer than 3 kilometers or has regions that are finer than 3 kilometers, you need that field to go to 0. And I'm not going to talk about those details in this talk, but they're relatively straightforward to handle to get that, to make them a little more resolution aware. So the disk averaging algorithm, and this is the fundamental change to the tool chain that will change the results. And we haven't, I'll show some preliminary results, but we haven't run it in the full model, so it's not completely validated yet. But this is a picture showing the 3 different types of algorithms. The red is the high-res lat-lon source grid. And cube to target does this incremental remap or area average approach where it has to compute all the intersections of each target cell, which is the black cell, with the background grid to compute the area, and then does an area weighted average over all the intersected regions. And those geometric calculations are what makes it incredibly expensive. The bin to cube is a very efficient algorithm, and it would probably work well for most of our applications, but the original Fortran code is limited to cube sphere target grids, not unstructured grids. And what that does is it, instead of this area weighted average, it finds all the grid points in the lat-lon grid that are inside the cell. So that's an easier calculation, and then just takes an average of the ones inside. And we replaced that because we wanted something even faster and to get rid of almost all the geometry. And we just replace it with a disk average. So we take that black cell, put down a disk with the same area of the black cell, but doesn't match exactly, and then just take all the points inside that disk. So it's just all the points within the radius given by the area of the target cell, and then you just straight up unweighted averaging. So the new tool chain looks like this. We have this 250 meter global source topography. We use this simple averaging or disk averaging approach, and we map from the source directly to the target grid. And then we also map from the source to the cube sphere grid, and from the cube sphere grid to the target grid. This path up on the top is now no longer used for the topography, but it's used to compute the SGH30 and SGH variances. So one of them is the variance between between the source grid and the 3 kilometer grid. And then another one is the variance between the 3 kilometer grid and the target grid. And when the target grid has regions that are finer than 3 kilometers, you can take, for example, you only work with filtered 3 kilometer data, and then the SGH computed with only filtered 3 kilometer data will automatically be 0 in the regions where it's finer than 3 kilometers. So this is the original topography that was creating these CFL problems and doesn't look appropriate for a 100 meter mesh. And then this is the new topography from the new tool chain. And this is so we have the code working, we generate the topography, we verified that. We've generated all the roughness fields, we haven't verified those, and then we haven't actually run it in a full AMIP style situation. Those are all next steps. And I will stop here. Thanks.
Questions?
Adam has a question in the room. I could just talk, right? Yeah. Hi, Mark. That's interesting. I don't think you covered any of the smoothing aspects. And so you're doing the smoothing on the this high resolution topography grid now?
So and this is one difference between E3SM and CDSM is we do die-core specific smoothing done by the die-core that's always on the target grid. So it doesn't actually, we do all this to get the unsmooth topography on the model grid. Then we apply die-core smoothing as a final step. So that's always, if you can afford to run the model, you can afford to run the die-core smoothing step. And then the variance, in particular, the variance between the 3 kilometer and the model grid is done with respect to the final smoothed topography, as in the original tool chain.
Explaining that.
Is the MBDA algorithm, is that all serial or are you running that in parallel?
It runs in parallel, but it doesn't have MPI. We run it on a single node using, as many cores. And I don't know internally how it's doing that, probably with threads.
Okay, but it runs really fast.
Yeah, we can do the biggest grid we've ever done, which is 33 million elements. So it's finer than our global 3 kilometer. And this 250 meter global data set, which is incredibly high resolution. It can do that in like 5 minutes, remapping on one node. So it's a simple disk approach. You could quibble with the numerics of it, but it is super fast.
I have a question, Peter. Why is it so fast? I mean, you still have to go and search for all the points within this little disk, right? Why is that so much cheaper than searching?
So since the source grid is a latitude longitude, you don't actually have to search because you know a point, and then you know the cloud of latitude points are within X distance. You immediately you can do that. You can do that search very super efficiently.
So this disk shrinks with like an unstructured grid. It shrinks down to
right. So it's the area of the grid. So
right.
You have some random point. Its area is 100 meters squared, and so you can quickly determine how many all the lat long points that would be contained in it.
Just a general question, to what extent are CSM and E3SM sharing any of these tools? And if we aren't, why aren't we, or should we?
We use the CDSM toolchain basically unchanged. We've tweaked the die-core smoothing part. So the toolchain is the cube to target and bin to cube are joint effort, led by NCAR. Gigi, when she did her work, found a couple of bugs that got pushed back into the NCAR repository. That's a good. I should have mentioned that to do that.
No, just
nice example.
Yep. So this thing could be pushed back to
yeah.
NCAR as well.
Yeah. This is just the toolchain doesn't really change, but you change the two Fortran.
Yeah, just wondering, we need to smooth the topography on that intermediate cube sphere grid for Julio to do a lot of rich stuff and so on. Would that be a complication if we start using some of your tool train?
There's one, so an interesting aspect of the algorithm which we haven't explored yet is the disk. You can increase this area larger than the cell, get more smoothing. So it is a parameter. It's a particular type of smoothing. It might not be the kind that you want, but it's a parameter that can arbitrarily do more or less smoothing in a resolution-aware way.
Okay. Alrighty. Thank you, Mark. Now we're ahead of schedule.
Should we just go ahead?
Yes, so next up is Patrick, who's going to talk about nudging in CAM.
Walk up slowly.
Yeah, walk up slowly.
You have 5 minutes to start your talk.
Okay, I was gonna wait for it to be 47 and then tick, 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 tick. Okay, so we're gonna talk about spectral nudging in CSM3 for unstructured grids. And so for spectral nudging, we want to selectively nudge the model's state variables to a horizontal scales larger than, what's this thing doing? Maybe we should, I don't want it to go. All right, yeah, so sorry, I was looking at a different frame. Yeah, so we want to selectively nudge values at scales larger than some specified value. And we treat those state values as a truncated sum of spherical harmonics. And then we truncate the number of harmonics based on some scale. So the rough estimate is just take the distance from pole to pole, divide by the number of points in latitude, and that's kind of gives the general scale for the nudging. So for the case we use is 500 kilometer nudging, which corresponds to a truncation of 40. So when doing the calculation of the spherical harmonic amplitudes for a typical rectilinear grid, if we do the surface integral by first doing an FFT along longitude grid, and then that is followed by a Gaussian quadrature in the latitude grid. Whereas for the unstructured approach, what we do is we replace that surface integral with just an area weighted sum over the unstructured grid points. So this approach also works for the rectilinear case because you can just treat it as if it's an unstructured grid and do the sum over its areas as well. So this form of doing the calculations is grid independent and so therefore is end up being dichord independent. So and for all these numerical approaches, as the grid resolution increases, of course, the numerical methods all return to the theoretical values in the end, but the rate at which they approach those theoretical values will be different for these two approaches. So, of course, the advantage of the rectilinear grid is it's robust, stable, well-developed, and generally well understood by the user community. The problem, of course, is that it is wasteful of computations at the poles, and the dichords that can use it are limited to those that have rectilinear grid formations. So the advantage of the unstructured grid is that it's dichord independent. It's also grid independent, where it's just fine for variable resolution grids, but it's not as computationally efficient. And there unfortunately are some very important non-uniform grid effects that appear. So to implement these spectral methods for computing spherical harmonics and zonal harmonics and all the related functions, a new utility module is added, and it supplies 4 classes for the computation of two-dimensional spherical harmonic analysis and synthesis, two-dimensional computation for zonal harmonics, and also can do the zonal harmonic analysis and synthesis for 1D latitude profiles. And then there's a zonal average option that does either bin averaging or can do linear weighting for linear interpolation of grid points in latitude. And so so these tools are not just for nudging, but they're also for other diagnostic applications as well. So with these tools, they have limitations that all the developers are going to have to be kind of aware of. The first is that the typical least squares approach of computing the spherical harmonic coefficients for the unstructured grid requires substantial resources and MPI communications. And so as a result, the nudge simulations at 500 kilometers are more than 5 times expensive than just in a nudge case. So that was kind of a steep cost. And so we did is we reworked that so it does a Gram-Schmidt orthogonalization of the theoretical basis functions. And doing it that way, we don't have to have all the resources that the covariance matrix needs. And so the 500 kilometer nudging simulation now costs a little bit less than twice as much as an unedged case. So the problem here is that with this case here is that the interpretation of what the amplitudes mean at the higher resolution modes. For the least squares effect approach, the numerical errors and the theoretical basis functions are distributed in the amplitudes across the modes according to the covariance values, and the numerical representation of the basis functions is not modified directly. Whereas for the Gram-Schmidt orthogonalization, due to the iterative method of its construction, numerical errors of the theoretical basis functions propagate down from the gravest modes down to the truncation modes. So the higher resolution basis functions from the Gram-Schmidt process end up being a distorted version of the theoretical case and don't actually accurately represent their original theoretical form. The second problem is that the use of unstructured or non-uniform grids is that they have significant effects on the resulting spectral amplitudes. I did a search on the internet for a figure that would kind of illustrate this problem, but all I could find was this well-annotated cartoon, which shows a test for a uniform grid with undersampling. So there's an alias peak there, and they compare that with that same case where the sampling is non-uniform. And so this shows that with the non-uniform grid, the aliasing is suppressed by the non-uniform constraints, but the true result peak can be distorted, and there's uniform spectral noise across the spectrum. Okay, so to see this in our SC grid approach, we look at some zonal mean spectral calculations versus the computational method. And of course, typically the most straightforward way of that approach that's used to deal with the non-uniform grids is to first fit or otherwise interpolate values onto a regular grid and then just use that regular grid. So along those lines, I have some results from a Wacom simulation for a given day for a spectral element grid, and then it has been interpolated into a lat-long grid with ESMF for methods. So these are our source data. So they're basically two different representations of the same state in two different grids. And so we want to compare four methods for computing the zonal spectrum. The first one is we take the uniform grid and just do the calculations of the typical way. So we average along the 180 latitudes and then compute the zonal spectrum from those average values in latitude. The second approach second option is to take that uniform grid and treat it as if it's an unstructured grid. So go through that whole machinery, compute the zonal spectrum directly from the 2D grid points, and then evaluate the averages from that spectrum. And then to do something similar with that, we take the unstructured grid and then do that process, compute the zonal spectrum for the unstructured grid and evaluate the averages. And then what I refer to as a 1D interpolation case is to take the unstructured grid, do a bin mapping onto a latitude grid with linear interpolation weights, and then compute the zonal spectrum from that bin average. So it's kind of a one-dimensional interpolation in latitude only. So on the left here, it shows what's considered the correct spectrum for the computed 2D rectilinear grid data. I say it's correct because it's just not necessarily absolutely correct. It's just what everyone considers to be correct because they're used to using it. To some extent, there might be some parts of this where the rectilinear perspective is not necessarily the right perspective. Maybe it's just you have a different framework in a unstructured grid where the how you represent things is naturally different. But anyhow, so on the right hand side, what I did is took the unstructured grid, processed it, and then looked at the differences between this reference spectrum. And so you can see here that the spectral differences due to the unstructured grid data are consistent with the cartoon figure in that there's a distortion of the resolve values shown at the lower modes, and then there's uniform spectral noise across all scales. So these figures here, I'm just showing the model levels as a function of basis index for levels above 10 hectopascals. So the other case is to process the rectilinear values in the same way using the unstructured grid as if it's an unstructured grid. And that shows that there are negligible differences from the reference spectra, which is good. So and then the last case is to do the 1D interpolation in latitude only. And so here the unstructured grid data is first linear interpolated to the latitude bins. Then the zonal spectra is calculated. The errors are suppressed somewhat, but not entirely. So in terms of the application, so for spectral nudging, the nudging module's been modified so that a new nameless values were added to control the spectral option. And then when it's active, the model state and the target state are both filtered using spherical harmonics, and then the tendencies for the nudging are computed from the differences in those filtered results. So the question is nudging affected by these grid errors? The short answer is no. So the result of Lagrange process is a complete orthonormal basis. So there's a one-to-one relationship between amplitudes and the grid values. And since the nudging is a linear process, any grid effects are common to the target and the model state, so they will not affect the difference results. But at higher truncations, there may be some artifacts due to the nature of the basis functions. But probably people won't go that far because the cost of the spectral nudging will increase dramatically with resolution. So you're probably not going to go down to those scales anyway. But there can be some distortion effects that might show up at some point. So in terms of the user standpoint, using spectral nudging only requires two additional nameless variables, one to turn it on and off, and the other to set the truncation. All the other windowing and existing nameless variables work just as before, and they're just applied to the spectrally filtered states. So use case, for the use case, we did simulations of Hurricane Maria. And for those simulations, we have a variable resolution grid at resolutions of 50 kilometers, 12 kilometers, and 25 kilometers. And a refinement domain extends from the mid-Pacific to the Ethiopian highlands in Africa. And these simulations were done as part of the Mesoamerican Affinity Group. And what we did is we did three simulations of Maria, one at each resolution, where the state of the models were initialized at the formation of Maria with ERA 5, and then ERA 5 boundary conditions were applied along the perimeter of our refinement domain. So the results of those simulations showed that we could see that, of course, the fidelity of the hurricanes increases with the resolution, but the tracks vary greatly with the resolution. So that leads to the fundamental question of how do you effectively compare resolution dependence in representation of these storm systems? So we, by applying 500 kilometer spectral nudging, we can selectively constrain the large scale state of the atmosphere while allowing the small scales and the parameterizations to evolve freely. And so when we apply the spectral nudging for these three cases, we see that for each resolution, spectral nudging drives the hurricane towards the true path of Maria. But it also, at the same time, it only has a marginal effect on the storm strength. So these nudging results give us results give us contemporaneous representations of the same storm system at each resolution. And shown here is Maria on September 20th for each resolution as it made landfall on Puerto Rico. And in the small figures there's little black arrows that kind of show the impact of the nudging and how much it had affected the position of the storm system. And the yellow lines indicate the location of the wind structure profiles on the right side of the screen. And so what we see is we have these contemporaneous profiles that give us insight into how Maria is represented by each resolution. So the nudging in this case here was applied to UV and temperature values. And shown here are the average nudging tendencies for the 2-week period of the Maria simulation at each resolution. And so for these spatial scales and temporal scales, the nudging values, I think, can provide useful information on scale dependence of bias. Now, if you looked at the tracking results for these Maria simulations, we see that there are other storm systems that were present. And if we compare those to the IB-TRACS results, we see that these representations are of actual storms that existed. So as part of the other simulations, as part of the MAG group, we did 3 year-long simulations of in our domain. In this case here, they were just free running with no boundary conditions, just running to see what storms, what the frequency of storms were and how they were formed, and comparing that to the actual observations. So given the results from Maria, we took the high resolution case and reran it with spectral nudging for August to September. And what we find is that every storm that's in the IB-TRACS appears to be present in the model. And there's some differences due to the tracking algorithms that pick up storms and drop them off because of 6 hourly versus 1 hourly data. But all the big storms are observed fairly well. And so this is, for me, this is one of these things that makes you say, So if we constrain the large scale motion of the atmosphere and specify the sea surface temperatures, then we see that all the actual storms appear when and where they were supposed to appear. So that makes me wonder even more, though, more so that that there's some useful information contained in those nudging tendencies that are maintaining that mean state, or that large scale state. So these results open up some new possibilities. So for a given storm, we can now curate simulations into a common storm-centric grid, which follows the hourly track of this data. And that will provide us with detailed analysis of how well storm dynamics are being represented across scales. Also, for a given storm track, we can now simulate ensembles of storms to systematically evaluate and model how the impacts of the impacts on the specific coastal regions vary with the strength and organization of the storms, which is useful for risk management. And I want to just end with nudging on saying that this works for, I say MPAS 2, but it should be CSM MPAS 2. So to validate that it works, I did a spectral nudging test of 500 kilometers on a S2S simulation of the Texas extreme cold event, and that worked fine. So it works for both SE and MPAS. So the other application of these tools is for the calculation of transverse Eulerian mean diagnostics. So if possible, we would like to use the spectral representation to facilitate the computation of derivative values in those calculations. But unlike nudging, these nonlinear calculations suffer from the effects of the non-uniform grid. This work is ongoing. We've done quite a bit of testing with different things to try and deal with the difficulties of the grid structure being treated spectrally. I don't have time to go into them because I didn't get it done this past weekend. But the following slides will show some of the results that illustrate the grid problems for U and for U prime, B prime calculations in the TM calculations. This might be one of those projects where you kind of eventually reach a point where you realize that you're whipping a dead horse. And so some of these grid problems might be insurmountable. And that's okay because we can at least fall back to doing an interpolation onto a 2D lat-long grid as a fallback. But, I still have a couple extra whips in my toolbox, so we'll keep going. So I think that, maybe it doesn't show up too well here, but in the lower left is the nice, clean, rectilinear grid view of the zonal mean winds on the grid. On the top, maybe you don't see the grid effect so much on this display, but this shows different problems with the U bar grid in terms of the actual grid that's being represented. And if we look at the differences on the left, it kind of highlights and pulls out what the difficulties are. You can see the grid structure and the latitude ripples in positive and negative values. And that's just a new bar. And then when you go to calculate the nonlinear term, you get all this kind of blotchiness that really distorts and makes the calculation kind of limited use. These are shown at the highest model level, which is the most problematic. So this is the worst of how bad it gets. On the right column, there's like some things you can do. So I've tried different things, and like I said, I still haven't run out of options yet. But so trying some different things that can suppress these errors to some extent, but I've not been able to eliminate them completely. So summary, spectral nudging is going to be added to CSM3 as simple name list options to use it. There's a new utility module for spectral methods and unstructured grids. It's also added that developers may find useful for their work, but they need to be careful and mindful of the limitations of these tools. So if I survive long enough, I will hopefully put in some future innovations. One is to put in a vector harmonic transform for some of these problems with the U and V winds might be because of the way the transforms are being treated. And I also add in vector operators so that the filtering of rotational and divergent winds can be nudged optionally. And I did put in, have an experiment test with replacing the basis functions with a doubly periodic basis. Gives a better partitioning between the vector and scalar symmetry over the poles. And then my ultimate goal for me was in doing this work is at some point to get a point to where I can nudge the amplitude and phase of the observed atmospheric modes and get back to some testing I was doing a long time ago. So there's many uses for this, and I'm hoping that some of you have already started thinking of how this can be useful in your work. And when I sit down and think about it, one that jumps out to me is this could be very valuable for S2S initiation methods. So with that, thank you.
Okay, questions for Patrick?
Any questions?
Patrick, thank you. This is very interesting. I was wondering how much the cost is affected by the truncation order. You truncate like order 10.
It grows because the number of modes, and you have to fit the modes in memory and then do the calculations. So for every n, there's a plus and minus m that's added, so it grows dramatically in cost as you go to higher truncations. So that's why I don't think I was getting into where they're worried about the distortions of the higher modes because it's going to cost too much to find that out.
And the 500 kilometer, is that is there any test like if you do the hurricane simulation, do you find like 500 is the optimal number, or maybe if you go to either bigger or smaller scales that?
We've only done like 4 or 5 tests, so 500 is good because it's a nice kind of separation between the chaotic weather scales and larger scales. But it was just that's just kind of what we expected.
Okay, let's try and stay on schedule since the lunch break is pretty short and move on to Xavier, who's going to talk about neural nets for convection.
Fine. Thanks. Okay, great. Okay, thank you so much for having me. I will try to keep this short so I don't delay lunch. So this work, I have to acknowledge that this is a group work. This will not be possible without the contributions of many people. And the goal of the research here is hybrid ESM. in specifically looking at improving convection in CAM6 using a neural network. So the motivation is pretty clear for, I think, everyone here. Deep convection is a key component of CAM6 and any other climate model, especially coarse grain climate model. And it's a well-known source of error and bias. There is a number of physically based representation of convection. CAM6 has one of the main representation, which is a plume-based model, the Zhang-Markov model. But of course, now we're at a stage where we can try to use our ML toolbox to try to improve that. So we could have gone, there are multiple ways to maybe approach the problem. We could have tried to use the Zhang-Markov scheme, for instance, and optimize the parameter, or maybe find a better convection triggering parameter in that scheme, so improve that scheme itself, or we could just move completely outside of that and do a data-driven scheme like a neural network, which is the approach that we're taken here. Of course, because it's a hybrid ESM, we have to be aware that when we introduce this new scheme, there may be masked error and biases that will be appearing more than with the Zhang-Markov scheme. So we'll have to see how it does. And this is where calibration is going to be very critical. So what we want to achieve here is we want to, first of all, produce a neural network scheme that represents deep convection. Then we want to basically port this neural network into CAM6. Specifically, we're going to be substituting the Zhang-Markov scheme, which is in CAM6, with this new scheme. And then we're going to try to calibrate this scheme to optimize the climatology. And hopefully things will be better on a range of timescales. So let's see. Okay, so we use basically what you could call would be the simplest architecture, which is a feed-forward neural network, which has 4 inputs, 2 profiles, and 2 scalars. So there is temperature and total moisture. So that would be vapor plus liquid plus ice phase together. This would be profiles from the surface to about 175 hectopascal, so most of the troposphere. And then, because we would like to have, of course, to know whether you're over land or ocean, we have a land fraction variable, and we also have a surface pressure variable, which is a proxy for topography. We have 5 layers. Each with 128 nodes, and we have 5 outputs, which are also profiles. Those are basically fluxes and tendencies that would be needed to close a thermodynamic and moisture budget. The way we design the neural network scheme is that we're producing fluxes like subgrid scale advectivity fluxes for energy and moisture and some microphysical variables like sedimentation flux for ice. And we do so such as to enforce conservation of moisture and energy. We also have tendencies which are primarily conversion of non-precipitating to precipitating phase of water and the energy released from it. And these are non-conservative processes. But overall, the way we design the scheme is to enforce conservation of moisture and energy. We trained that neural network on a high resolution diamond experiments simulation. So we use the GSAM global system for atmospheric modeling simulation, where I guess I say 4 kilometer and 2 kilometer. I think it depends exactly the area we're looking at, but it's a very high resolution. It's not convective resolving per se, but it's much higher resolution, of course, than CSM. And because it's a very expensive simulation and it will need a lot of storage, we use only 1 month of data to train the model. So 30 days using hourly frames. We're using specifically the month of January for this. The way we do the training is that we coarse grain that high resolution output onto our CAM6 resolution grid of about 100 kilometer. And then we partition grid mean and subgrid scale. And we then train the model using this coarse graining. The way we implement this neural network in CAM6 is a multi-stage process. Basically, first step is that you take the CAM state variables, you transform that into your GSAM state variables. The GSAM use this non-liquid static energy and total moisture. Then we regrid into the GSAM vertical coordinates. Then we run for the neural network, which provides us the fluxes and tendencies, which are then gridded back onto the CAM grid. And then that allows us to compute the net tendencies in moisture and energy, which then bring us to the next state of the energy and moisture through a simple summation. Why we do this regridding thing? Well, of course, it's because we train the model on a very specific data set that has its own vertical resolution. And when we use CAM, if we want to use different spatial resolution, we don't want to have to retrain every time the model to be able to use a different resolution in CAM. So we took the approach of using the native resolution and doing this regridded back and forth. Yeah. So I think a big caveat in any hybrid ESM experiment is that we're swapping here one specific scheme, that's the Zhang-Markvanén scheme, with our neural network scheme. But all the other schemes are active. And when we do training like on GSAM or on any other variables, we would not be able to separate cleanly what would be the equivalent of those schemes doing in that other model. So there will be likely some overlap, and it's not a perfect system in terms of the way we implement it. We specifically try to do our best to really train and output variables that are specific to the subgrid scale. So we don't interfere with other schemes like the grid scale, like MG scheme, for instance. So to evaluate the performance of our scheme, I think there would be a wide range of metric we could be using. I was very interested by Rich Neal's talk because he had like very many nice diagnostics. So I have to inspire myself from that. But here I'm only going to show a few diagnostics. Some of them are climatological, some of them are about the PDF of rainfall, and some of them are about subseasonal synaptic scale, tropical wave diagnostics. So here I'm going to do, in most slides, I'm going to show you 3 different setups of CAM6. One is your out-of-the-box CAM6 with Zhang-Markvanén. The other one is a CAM6 version where I turn off completely convection. And the other one is CAM6 with our neural network convection. The reason I use the off convection is that sometimes it's you'll find that some variables actually or diagnostics are not so much impacted by convection, and others are very impacted by convection. So it's a good way to kind of see where you are. And on top of that, of course, and that's maybe the most important thing, we're going to comparable observation. So here I'm outlining a few of the observational data sets I'll be showing you today. So let's first look at the basic kind of precipitation climatology. So on your left, you have the zonal mean, annual mean climatology for a 4-year average. I've used a historical run, by the way, 2010 to 2014, using the F-East COMSET, so the historical, forcings, 2010 to 2014. So all these things are 4-year averages. And so the annual mean zonal mean precipitation has multiple lines. There is a observation line, which is GPCP here, the blue line. There is your the ZM, that's your CAM6, default CAM6, which is fairly close to the observation, I would say, especially in the deep tropics. And then you have our neural network, and there is also the off case. As you can see, the off case doesn't do so badly. So this is, clearly a diagnostics where maybe you might think that having a convection scheme doesn't change greatly the situation. The most important thing here is that our neural network seem to do a fairly decent job at capturing the extratropical to deep tropical variability. We're not really expecting to do better than ZM because CAM6 has been tuned to do a good job with this sort of metric, but at least it's to show you that with basically no tuning that we've done, we already obtained something which is pretty reasonable in terms of the climatology. Now on the right, you will see the intensive frequency diagram for precipitation. So this is actually give us hope that what we're doing is maybe a step forward. So you can see that the blue is observation. So here I used iMerge 3-hourly. The red is the ZM CAM6. The green is our neural network, and the black is no convection. So you can see that, and that's a thing that have been shown by a number of people already, is that ZM has these known biases where it tends to drizzle too much and also tends to underestimate the most intense frequency extreme events, I guess. We seem to do a little better, especially on the extreme end. We still, I think, drizzle too much, but maybe on the less drizzly part of the drizzle, maybe we're doing a little better. Yeah. So I think that's pretty good. Okay, now I'm going to show you some humidity and cloud cover variables, and I think here I'm showing you this slide primarily to tell you that sometimes it's difficult to know, it's difficult to improve things beyond, what we can in CAM6. Because for instance, if you look at cloud cover, you can see that compared to observation, which is that GeoProf diagram here, we underestimate, ZM CAM6 tends to underestimate pretty strongly cloud cover. Our scheme also, of course, and the no convection also underestimate cloud cover. So it's something here, for instance, that we would struggle to improve in any case, regardless of what you would do with the convection scheme. In terms of the humidity profile, it seems that it is, I think, I don't know if we're doing better or worse. I would say probably ZM is still a little better overall than all these other cases. But you can see that maybe we're struggling a little bit in the lower part of the troposphere, and that's most likely because we're here having some interaction with club scheme, which is also a problem that we have, is that we have to be mindful about this competition or overlapping between different schemes. Okay, now let's look at the diurnal cycle. You have observation. Okay, so the plots on your left are the peak hour from 0 to 24. You have observation, you have your ZM-CAM6, you have no convection, and you have neural network. I would say that compared to observation, they all have their issues, but clearly having a convection scheme is important, as you can see from the off case, especially over land. Less important over ocean, but especially over land. You can see that the neural networks seem to do somewhat better, especially and maybe somewhat surprisingly over the mid-latitude region. We're still somewhat struggling in the tropics. So especially over land, you can see that when I do the average for the tropical lands, diurnal cycle, we tend to over precipitate during the night. Although we do capture the diurnal peak around like 4 p.m., we over precipitate during the night. So there is an issue, that's for sure. And that issue might have to do with what is shown on the lower panel on the right, which is this is the GSAM training that was done, and the green line is basically what if you run GSAM with that neural network that you trained in GSAM, and you can see that there is some also very strong precip overnight, which is also not correct. So there might be some issue with the training here. But overall, it's not so bad. I think we're doing something right in some regions. Now I would like to conclude with tropical waves and MJO. So the top panels is the symmetric component for the Wheeler-Kiladis diagram. This actually is from Brian Medeiros' GitHub page, so thanks for that. There is observation using daily, and then there is the same diagram using 6-hourly. You can see that the Zeng-Markfarnen doesn't have enough tropical wave activity, basically, especially, I guess, in that Kelvin wave, range. The neural network has more of that activity, but like ZM, we seem to somewhat miss out on the MJO signal. Now let's look more specifically at the MJO. So here I'm showing you a lead lag plot. So the y-axis is lead lag in number of days, and then this is the longitude from 0 to 350. So basically 100 would be, I guess, around the maritime continent. You can see that, so in observation, like in IMERGE, you see this very nicely propagating signal, which is your MJO. In ZM, you don't really see that. It seems a lot of it gets killed over the maritime continent. And then in our neural network case, it's somewhat in between. So we don't get something like observation, but we get something a little there. So, that's, I would say, somewhat promising. So in summary, we've built this neural network. We've trained it on a high-resolution GSAM simulation. With little tuning, we're doing okay in some of the, I would say, hard-to-get metric, but there's still work to do. We're still not there, especially the diurnal cycle is still somewhat off in the tropics. And also, most importantly, we're right now we're also focusing on seeing what would be the tunable parameters in our scheme so we can better calibrate our model in CAM6. And with this, I would like to thank you. And I also would like to mention that we have an F-torch implementation of that scheme coming, thanks to Adisu. Thank you.
And any questions in the room?
I'm just curious. So the way that precipitation is being represented in this or manifesting in this neural network is if the total water changes because the total water is just vapor and cloud. So if if there's a tendency of total water, that must be an auto conversion.
Yeah. So one of the term which is one of the outputs of the neural network is the auto conversion term, and that's at every physical time step you output a auto conversion term, which is a profile, and you can simply integrate in the column, and the net of that will be precipitation.
Gotcha.
Yeah.
It would be interesting to see precipitation, broken up between the one produced by MG and the one produced by the neural network.
Yes, yes, it actually gave you a very different response, including, for instance, if you look at the Darn cycle over land, for instance. Yeah, that's true. That's a great suggestion.
I have a quick question. I mean, ignoring the complications of having physics that looks at multiple columns, have you thought about training? It seems like you're training on one single column of T and Q.
Mm-hmm.
Have you thought about training on a stencil?
Yeah, we thought about it, but we never pushed that forward. I think there were previous studies that did look at that, not in great detail, but there is, for instance, some past work by Paul Gorman and others who looked into that specific area, whether having perhaps surrounding columns would be important. It seems that the evidence for it is like not supporting that, but I think we have to improve maybe, especially if we still struggle with some of those metrics to perhaps try that.
Okay. Let's break for lunch, and then we'll be back again at 1:10.
Yeah, so I thought it'd be useful to give a summary of some of the sensitivity to the ZM convective particle temperature exercise we've been through. Pretty simple, but pretty illuminating in terms of how the model behaves. So background is we've increased vertical layers in CAM7 from CAM6 to 58. Many in the boundary layer, a thinner, quite substantial near surface boundary layer thickness. But what I'll show is that we need to make a modification because there are sensitivities that are kind of undesirable. And this, in the end, reduces near sensitivity to near surface level thickness, but shallows the convection. So the kind of latter part of the presentation will be trying to understand how we can make it deeper, which seems to be the perpetual problem. And we've done some single value investigations, but what I'm trying to do now is to do a little bit more complex kind of properties specification for ZM to see if we can maintain some of these desirable signals. So in terms of vertical levels on the right there, CAM7 is the red, that's the level thicknesses in the numbers, and then CAM6 with 32 levels essentially is in the blue. So the key thing here is right near the surface, CAM7 now has depends where you do it, of order 30-something meter layer thickness, that's thickness. So the center is around 20-ish. And that compares to 114 meters thickness. So the question is, how does a deconvection scheme, all things being equal, you just give it the scheme that as is, how does that respond? And so I've shown this before, but we can do single column model experiments. And if we look at some parameters in terms of the way the convection is behaving near the surface, so on the bottom left here is essentially a PDF at different vertical resolutions, and we can see here 32, 48, that's without the boundary layer levels, and then 58 is with the new boundary layer, and then 256 is the extreme case, just to see the non-convergent behavior. And you can see quite clearly, if we were to look at instantaneous values from single column model, and we, like I say, put them in a PDF, we can see that the temperature tendencies that come from the scheme just get more and more severe the more finer the vertical thickness is, particularly near the surface here. So we've got things out to 50 Kelvin per day.
I mean, you don't really see it if you look at precipitation in a similar way, just PDF of preset values in the single column model here, total core, by the way. There's not really it's obvious that it's there. But if you look at something like club, and you say, what is club doing in that lowest model level? And then you can see that there's, opposite sign, same magnitude compensation in that lowest layer. So there's a compensation in that lowest layer that just gets more and more extreme with more vertical levels, in particular the level near the surface. So we made a change to how to kind of ameliorate that. We made a change of how the convection scheme generates parcel properties. So on the left there, that's essentially the way that ZM behaved before CAM7, so in CAM6 and models versions previously. And basically, without going into too much detail, it determined the parcel properties almost exclusively as that of the lowest model level, essentially the moist static energy H here, and then use that to perform a vertical profile of buoyancy and get a cape, for example. But of course, the thinner and thinner you make that level, then you kind of, what tends to happen is your properties of that level tend to get warmer and warmer, but probably more consequential is downdrafts then tend to populate that thinner and thinner layer. That's probably why you get those extreme sensitivities. So to offset that on the right-hand side, we did essentially a parcel calculation that was more of an average of the moist static energy within the boundary layer over some, well, it's not necessarily within the boundary, it's over some thickness. And then that was of order half the depth of the boundary layer. So that makes it somewhat much more insensitive to that very lowest model level thickness. And if we go back to this plot here, that was what I showed previously, and that's without the modification. And now if we jump to this modification, we can see that, it's much more, given the same profiles within the single column experiment, then we're subject to much less variation in that parcel temperature near the surface. So it's much more, convergent. So we have this modification, but of course the consequence of that is that, as we talked about, is that convection is too shallow now. So I've been looking at this, trying to add enhancements to the parcel that is used, parcel temperature properties that is used essentially to initiate the ZM scheme with a particular parcel properties that it ascends through the atmosphere to determine buoyancy. But what we have there, just a simple equation here, is buoyancy is a temperature represented by temperature, virtual temperature here, has some property already added to it, this Tiedemann add, and that's been in the model for many, many years, and it's currently, I think it's, as far as I know, always been about half a Kelvin. And so, these have been included in some of the PPE experiments, trying to investigate the differences. So it's not new in terms of thinking that this could vary. A second possibility is this what's called a TPERT parameter. And in some ways, this is more desirable to think about parcel temperatures for deep convection, as it has originated from the boundary layer schemes within the model in the past. Now, for CAM4 and CAM5, this was true, and it used people familiar, Holzlab-Bovell and the UW schemes. But unless I'm wrong, which is not unlikely, CAM6 and CAM7 does not use a value of this particular parameter from Club. So Club does not supply this extra enhancement TPERT. So I've tried to hopefully I've connected that in. I just have one plot at the end to see how that works. So I have a number of experiments coming up, and they tend to be adding a temperature that's 0 Kelvin, so going in one direction, parcel is cooler, and then all the way through to 1.5, but 1, 2, 3 Kelvin. And so what I'm showing here is the convective depth. So the top of the convection here in CAM7 with this default 0.5. And we're looking at, over the oceans with topography, we're looking at maybe 600 millibars, maybe less, 650. So that's low, one would imagine, for deep convection. It's a pretty low value. And then if we step through these sensitivity experiments for 0 Kelvin, then the depth of the convection is lower. We don't want that, obviously, by the flip side, of course, millibar, 80 millibar lower. But then when we step through these different values of TICA, then there's predominantly a linear part, as in, convection gets more deeper. as we really step it up to 3K, there are regional, you'll see later, but regional differences that kind of offset any local, just simple, the circulation response offsets that from a local, response to the cloud top. If we look at those simulations, and we're looking at things like precipitation, this is zonal mean precip over the ocean. And so we can see couple of observations here, and then, these successively stepping through these individual simulations. And so red here is, the control, and we're, overestimating precip that is perpetual common problem by 10% or more. And so one can imagine, as I put in the title, we kind of have a excessive water cycle in the model. And then if we step through and look at the 3 Kelvin one, which we're not thinking that that's necessarily viable given some of the responses we'll see, but we'll clearly see there is a sensitivity such that it's a much more accurate precipitation within the model. So it would, as we look later, it seems more reasonable that maybe 1.5 or 2 Kelvin could be considered a more attractive possibility. Now, of course, in concert with that, like I say, the water cycle, if we look at the latent heat flux, now we really do see significant improvements. They're definitely improvements, but whether they stand alone is another question. And so we have always had this excessive latent heat flux in the subtropics here. And so in latent heat flux in subtropics, tidal circulation, ITCZ, it makes a lot of sense. But with these changes, particularly as we go to 2 Kelvin and beyond, we're reducing the latent heat flux consistent with the precip, of course. And then finally, as part of the state of the water cycle is the precipitable water. So the water in the column through the tropics. And the same story kind of comes out, which is we have too much water in general in the control here. You can just see the black line here is an observational product. And so, but then if we step through, again, this 2 Kelvin looks about right in terms of these variables. So, the whole water cycle is spun up. If I look at surface stress, I haven't shown it here, it's the same. So it's not a surface stress difference. It seems to be something in the way that convection is extracting or moisture from the lowest model level. I haven't looked at it in detail yet, but that seems to be the kind of, the canary in the coal mine, but it doesn't necessarily mean it's a bad thing. Another attractive part of this is precipitation over orography. And so this, again, stepping through some of these simulations, precip, top left there. And so, there is no maxima really in precip over the Andes, but CAM7 has this whopping great, precip sit right on top of the Andes. And so 0 Kelvin is as bad or worse because that's, like I say, tends to be going in the opposite direction to what you want. But stepping through these particular simulations seems you are reducing the precip here. It's not as noticeable as the next one, which is over the monsoon region. So if we look at the precipitation biases over the monsoon region, this is the other orographic kind of pain in the where that it's been for a long, long time. So precip right over the top of the Himalayas. But if we step through these increases in TPA, we really get some noticeable, region-wide improvements. I mean, just picking out this value, for example, is, 2.78 root mean squared error compared to 3.08 in CAM7. So there are noticeable improvements, and I think Leo and others have said this. I haven't seen this kind of reduction over topography from this mechanism. Oh gosh, I'm running out of time. So no good deed goes unpunished, unfortunately. But because if we now look at other aspects of the water cycle, other aspects of the variability in particular, we tend to see a common kind of response of change in the convection, which is, I've showed these before, hopefully I don't have to go through them again, but these are an estimate of the tropical wave variability. So I'll say that for long waves, short waves and short periods and long periods. So CAM7 on the bottom left here compared to 2 observation products on the top looks pretty good. And that's one of the good things about CAM7. But the sensitivity to their changes in TICA are clear, particularly too clear. You're really reducing this, at least it's assessed to background variability. So one thing I've just recently started doing is thinking about the better ways we can like prime this surface temperature, possible surface temperature, other than just specifying a single value. And so one way we've tried is to kind of link it to both orography, which turns out to be probably not that great, but also subgrid scale orography. So, we have the subgrid scale orography here, for instance. You can always tell it's subgrid scale because Greenland has this ring around it rather than orography on top. But it looks similar to orography, of course. But and these are the parcel temperatures based on some very simple scaling of the orographic height to a parcel temperature. So we're going to employ this to specify the parcel temperature in the model. And so this is too much, but like essentially I've gone through a series of experiments. This is throughout the globe where, these are the constant ones I've just talked about. So 1, 2, 3 Kelvin everywhere. And then we're specifying something over the atmosphere, ocean, something over land, and then potentially something over orography. This is CAM7. It's all the same. So this is an example. We're specifying something that we just retain the temperature, parcel temperature higher over land and keep it to the default. And then these bottom few, essentially, now we're specifying over orography something that's a function of height, and then bottom right is something that's a function of subgrid scale height. So that's it. So I only got one plot, and then I'm kind of done with the summary. And so this is showing these preset biases again. We have CAM6 in this case and CAM7. It's a good example to show that CAM7 is actually not as good as CAM6. And then 3 initial looks at specifying that parcel temperature in a number of different ways. Oh, and the bottom left one there, just as a reminder, is if we have that 2K fixed everywhere, these are wrong, ignore these numbers, 2K fixed everywhere. But this one here is if we specify 3K over the land and not over the ocean. And for this, a lot of things are changing. Obviously, a lot of differences here, it's good and bad. But this seems to be responsible for, by doing this, we remove this Himalayan maxima, which is interesting. I don't quite understand exactly why that is. And this, in a similar vein, this is when we use the subgrid scale precipitation. And it's hard to see, but the actual Himalayan maxima here is off the main top of the Himalayas, on top of the variance in the orography, which makes a lot of sense. Very, very final plot is I've just implemented a way of just reconnected this temperature perturbation that should come from the boundary layer. And I'm a little suspicious that it actually looks pretty good. And this is just the first incarnation of this. So this is more ideal. If we could get this to work and be more related to what the model is saying from CLUB in terms of the parcel, the boundary layer tendencies that dictate, the initial parcel temperatures. So finally, sorry I've overrun, but CAM7 required these modifications because of the sensitivity, but we need to increase depth still. And when we do that, we get some good things, water cycle, orographic precipitation, but unfortunately, tropical wave variability. And so we're in the middle of trying to say, can we finesse that with what happens over land versus orography? So that will be, it's pretty promising, I think. We'll see what happens. And then this is another effort, actually, I thought I'd mention this that Ren talked about. We have other ways to kind of do this in partnership with understanding the chemistry of Southeast Asia. Yeah, thanks.
We have time for some questions, and people online, please raise your hand or put something in the chat. I'll try to monitor that. Mark?
You mentioned SGH30. It's been mentioned a couple of times.
Yeah.
How do you decide if you're going to use SGH30 or SGH? And are there any parameterizations that still use SGH?
That's a good question. I mean, we talked about this when we said SGH30 is 3 kilometers.
SGH30 is kind of more scale.
Yeah.
I mean, it's resolution independent.
Right.
Yeah. But what are the boundary layer eddies is influenced by the topography length scales? It's hundreds of kilometers. It's one could imagine you could come up with something that's much smaller, actually, scale wise. But good point.
It doesn't look like there's anything online. If I'm missing it, please pipe up. I had a question when you spin down the water cycle with Tidkiad, do you know whether it's spinning down convective or large scale precip?
I don't know. I've got the plots, but yeah.
The MJO variability goes down.
That's totally true. Often that's another thing that I mentioned.
Well, oftentimes when you do these things, it's the balance between the two. I should let you know.
Oh, okay. Chris, try ask the same question. Okay.
Good question.
Great question.
Yeah, there's two questions on it. I'll look at it.
All right, thanks, Rich. Next talk is by Cecile from quarter degree simulations.
Okay. Okay, then I'm going to talk about recent CAM7 resolution, high resolution simulation that we have been doing. And I swear it's recent, even that I just noticed it seems to be the talk of last year on February 2nd, 2025. I got it all wrong because I think we are the fourth. Anyway, this is mainly the people who put plot on this presentation. It's Julio, me, and Rich. And then, but we have other people involved in this study. Then there are Ben and Colin that are looking at hurricane, Vincent Larson, and then people from Texas, Dan Fu, Pink, and Shu, and then Andre and Pace, because we are using one of his tools. And the roadmap for his talk, first I will talk about the motivation, we'll show some large-scale precipitation, then I will touch tropical variability and diurnal cycle, and I will show mesoscale system, tropical cyclone, and I will try to show you what improve at high resolution and what doesn't. But before we do anything, I want to give you a warning. And I remove the NSF NCAR sign. Because yesterday at 6:26 a.m., we got this message that said to a scheduled surprise. It didn't say scheduled surprise. It was a schedule. Seems it was scheduled, but it was a surprise for all of us. We temporarily lost our ability to do science. Then after the machine came back last night, and then I received plot of Julio at midnight, and Rich 6 a.m. is contacting me. But unfortunately, we were not able to generate all the plane figure. Then anything missing plot is this talk has been replaced by a cat picture. This is Moshi, and this is, yeah. Okay, then the motivation. And basically, the way we started to do this CAM at high resolution, it's a collaboration between us and the University of Texas A&M, and we have generating two twin high resolution simulation with the same output, one with CAM5 done by Texas and one with CAM7 done by us. And then this simulation, before we had done like 10-year simulation, this simulation were longer. It was 20-year simulation because we wanted to get better statistic. And we have done the high resolution, but I also did, at least for the CAM7, I did a 1-degree companion simulation. And for this, we have used not the traditional SST product that we have been using. We have been using prescribed SST it's a native resolution of 1/20th degree, and it's daily. And we have been interpolating this on a 1/4 degree grid. And this is the SST that we are using. And basically our focus, it's the tropical cyclone, the mesoscale phenomena, and the extreme precipitation. And we have used several trackers for this. Then one of the trackers is the MOAP, it's multi-object analysis of atmosphere phenomena, and it allows to identify and track several mesoscale features like the mesoscale convective system, the tropical and extratropical cyclone, front jet stream. There are a lot of stuff
that you can track with this. It's an open source tool that you can find there, and the reference is over here. And for the tropical cyclone tracker, it's not me, it's other people, have used the Tempest Extreme and cyclone metric package to track the storm statistic and the tropical cyclone. First thing that I want to show here, it's the mean precipitation in CAM7, comparing the IRES in the middle column and the low-res on the far right. I'm the opposite, then it's the right. On the right side, then you see that in the low-res, we act like, I don't know, there's nothing to point. Okay, anyway, you see that in the low res, there is like big red blob. And then this improve in the IRES simulation. But then you see that on the other hand, you have a beautiful double ITC zinc showing up in our IRES simulation. And then we compare this with CAM5. Then here now the middle is still CAM7 IRES, but now on the right side it's CAM5 IRES. And I would say that overall the mean seasonal precipitation looks slightly better in CAM5 than they are now in CAM7. And now this is a plot of the convective precipitation fraction, and here again on the right it's the low resolution, on the left it's the high resolution, and then you see that the precipitation fraction really decrease, the convective precipitation fraction really decrease when you go to high resolution. It's because you start to resolve some of the convection at high resolution. Picture from Rich, then this is the MGO in CAM7. On the left, this is GPCP ERA interim. On the middle, it's the low res, and on the right, it's the high res. And you see that, unfortunately, it's poor performance, both at low and high resolution. And there is like no improvement at all. And then Rich said that maybe the simulation without the deep convection might be better. Then we wanted also compare with CAM5, but it's when we got hit. Rich got hit. He told me this morning he cannot. You told me that you could not do this plot with CAM5 because you were having problem with stuff that were not working. Then he sent me a cat picture. This is not my cat picture. It was Rich. And then 10 minutes later, he sent me another email. He said, I had an issue, and I did something wrong, and I saw he's going to send me a plot. No, he sent me another cat picture that looks like my cat. Then I really appreciate. Then anyway, we don't have the comparison with CAM5, but maybe Rich can tell how you're supposed to. Okay, then it will be as bad. Yeah. Okay. Diurnal cycle. Rich showed this 2 days ago. He showed some of the diurnal cycle. Then if you're not familiar with this plot, then first on the left it's stream, the middle is high resolution, on the right is low resolution. And then I forgot to put, I cut by mistake okay, I'm sorry, it doesn't show the timing, but this shows you the timing of the precipitation. And if the color are different, it means that you are not getting the timing of the precipitation. And you have also the intensity of the color. It shows you if you are getting the right intensity of the precipitation, the amplitude of the precipitation. Then you see that in the high resolution, the diurnal cycle is much improved in many of the regions, but there are still like issue, like for example, over India, where we don't have so much improvement. And I'm not going to go too much on this because Rich already touched about this. Then this is now a plot that shows the MOAP analysis in CAM7. And this is a really cool plot because this gives a summary of many mesoscale features in one single plot. And this is here the ERA5. In the middle, it's the CAM7, and on the left, CAM7 at high resolution, on the right, CAM7 at 1 degree. And what I want you to look at here, then the x-axis, it's the horizontal length scale, and on the y-axis, it's the time. And let's focus on the MCS, it's the green plot. And you see that at low resolution, then this is, I'm not going to touch the screen, so I would be in trouble, but this is the green dot. You see that at low resolution, we were not having it right at all. The timing was wrong, and especially the time scale was wrong. And when you look at the CAM7 at high resolution, it's doing much better. And if you look at other feature, then there are also other things that are improved, even if not everything is right. And we have been starting to look at this. But what's really cool about this is that when you do this MOAP analysis, it allows you to have it track many objects, and then you can look at them separately. And this is an example what you could look at. This is the mesoscale convective system. Once again, observation is on the right. Then you see where you have the MCS track by this tool on observation. And then if you look at the low resolution, you don't have any MCS at all, but in the middle, you have the CAM7 high resolution, and you see that we don't see everything, but you see much more MCS than in the low resolution. And you can also track, for example, you can look at the precipitation that are associated with the MCS. And here you see on the, again, it's the same low, resolution. Sometimes it's one way, sometimes the other, but depends who did the plot. But this is low resolution, in the middle, high resolution observation on the right. Then you see the MCS object and the fraction of precipitation that contribute to MCS object. And on the bottom column, it's the precipitation contributed by the MCS object. Then the first thing you can see is that in the tropic, it's mainly the MCS that contribute to the precipitation. And then now you see once again that at low resolution, you don't get this at all, but at the high resolution, you start to track this a little bit better. Another thing that Julio has been looking at is the precipitation associated with equatorial wave. Then once again, this MOAP tool have like several objects, and you can see the Kelvin wave associated with precip, the Rossby wave, the equatorial Rossby wave associated with precip, and the mixed Rossby gravity wave associated with precip. And what's nice over here is that you see that in the middle column, some of the wave associated with precip, it seems that you have some picture of the double ITCZ, some signature of the double ITCZ that appear in this figure. Okay, then this is what I get. This computer want to update. I hope it's not going to close on me. Okay, then I'm stuck because it wants to update. I just say no. Later. Okay. Oh, now he wants to update PowerPoint. Later. Okay. No, it's fine. I think it was telling me I want to update, and then I was stuck. Oh, okay. Yeah. Okay. Thank you. Thank you so much. Yeah. Okay. Then. It's still not. Oh yeah, no, it's not moving. Okay, no, it's moving now. Okay. Okay, then now we are moving to the tropical cyclone and. Oops. Thank you. You should not have given me this stuff. Okay. Sorry. There is no red button. Okay, then I'm going to try this button. Oh yeah, look, it's magic. Okay, then this plot here show you, then Ben show a lot of things about the tropical cyclone, and I'm going to show just a couple of slides here. Then this plot is the accumulated cyclone energy density. And here this was how it was in Camp 5, it's how it's in Camp 7, and this is how it is on observation. And it's again a plot produced by Julio, and he separates here in different regions. Then you see the different region, North Indian, Northwest Pacific, etc. And then what's interesting here, it's then you look at the different region, and I tried, this was really small here, then I tried to make the label of the x-axis a little bit bigger. Then you see here the light blue compared to the red. It was Camp 5 compared to observation. And you see that in most of the basin over here, we were underestimating the ACE. Then, except maybe in the Northeast Pacific, where Camp 5 was doing a fairly good job. Then once we go to Camp 7, we are doing much better. We have increased, even that in some of the basin we overshoot. Now we overshoot the ACE. But yeah, this shows the different basin. You see then, for example, the basin here where we overshoot over here. In the observation, we were like this. Then this is the Northeast Pacific. Then we were doing more or less right in Camp 5, and now we are completely overshooting in Camp 7. But otherwise, it's getting better in Camp 7 overall. Another plot that Ben showed yesterday, but I saw I would add this here. Then this is like, if you look at other tropical cyclone matrix, it shows much improved behavior in a Camp 7 that in Camp 5, and in particular here, it's showing the storm count bias. This is in Camp 5 and this is in Camp 7. Then it seemed in Camp 5 the bias was quite large, and in this version that I'm showing here, then it's much improved. Then basically, this is what I have. Then my conclusion that this is still like preliminary result, but what improved, what doesn't, that I hope I have convinced you that the high resolution clearly changed the character of Camp 7. What improved at quarter degree, we have a better diurnal cycle, both in phase and amplitude. We have more realistic MCS climatology that were completely absent at low resolution. We have also improved mesoscale organization that's captured by MOAP. And the tropical cyclone structure and the ACE distribution are improved compared to what they were in Camp 5. What doesn't improve, you have like double ITCC tendency that emerge in the high resolution run. The MGO is poorly represented in low resolution, high resolution. Then it means resolution alone is not sufficient to improve the MGO. And also the MCS rainfall is still underestimated in key regions, for example, in the central US. Then I want to say also, the more the better. Then in the spirit of the atmospheric working group, you can contact me if you are interested to analyze any aspect of the simulation, and you can have add your name here to this list of people. And I have this little asterisk because it's especially true if you like cats. Picture. Okay. Any question? Then, yeah.
And online, please just pipe up. Are there questions? Yeah, Rich.
I asked you this yesterday, I think, anyway. But how do you think Camp 5, Camp 7 would perform if you had the same time step at low resolution? I'm wondering.
Yeah, I told you that it would be very easy. When Rich was interested to see when we do this kind of plot out, it will change. It will be easy. We haven't done this because the machine was down. Otherwise, I was going to do it last time. But then, yeah. It would be easy to do, and it would be interesting to do. I have no clue how it will change.
Yeah. I don't either.
I don't either. You have a clue, Rich?
I mean, the MCS looks like it's spatial more than temporal, the improvement.
Right.
But, you know. Anyway, Adam, sorry, I didn't mean to jump in.
If we could stay on this slide, actually. So this is the Moab diagnostic, right?
Yes.
Is that Andreas Preen's diagnostic package, or was that Ping's? Because I saw both of their names on your co-author list.
I think it's Pink who just create this plot based on.
Ping started making these plots, but it's based, the inspiration is, I mean, it's from a paper that Andreas wrote looking at observations.
Yeah.
So Andreas made basically the ERA5 plot that also uses, I forgot exactly what observations to diagnose precip and surface temp or something. But yeah, the ERA5 is basically Andreas, then Ping started applying this to the quarter degree.
Okay, so I mean, if I were to do this, I'd have to do like one circle comparison plot because it's very hard to figure out what's going on. But the green is the MCSs, and you're saying it's shifted to the left, and so it's it's representing it's smaller horizontal length scales in quarter degree than MCS is represented in 1 degree. Okay. That's all.
Yeah, and I have a lot. If you're interested to look at this, I have
Good scripts?
script over here. And,
All right, cool.
okay.
Thank you. I think Xavier had a question.
Oh, sorry, go ahead. No, I didn't see. No, please.
But I was so would you say it's fair to say that despite the fact that you have quite a bit of improvement in like tropical waves and like MCS and things like that, but you don't have improvement in the diurnal cycle? Is that a fair statement to say, or like
between what and what?
Between when you compare Cam 5 and Cam 7? Like
I haven't looked at the diurnal cycle of Cam 5 compared to Cam 7 because we edited. Yet a cap picture for the
I don't think it's going to be that different. Maybe there's some amplitude difference, but the timing, I doubt, would be significantly better or worse. Yeah.
So whatever you've done to improve these other things does not relate necessarily to diurnal.
Yeah, I mean, convention, apart from that, what I showed there hasn't really changed. Its response in the system will be the same pretty much. In resolution differences and in model differences. There's nothing, I don't think there's anything fundamentally that you're resolving better between those two resolutions that would help. I don't think. Well, I mean, I'm talking about the large scale precip, but I don't.
MCSs might contribute to a better diurnal cycle somewhere, maybe not over the central US where we don't still seem to get them. But.
Yeah, definitely not.
All right. I think, we're starting to get behind, so maybe we should, thanks Cecile again, and move on to Vince's talk. Vince is online.
Great. Let me share my screen here. Okay. It should be shared. All right. Is that visible?
Yep. But
okay.
We're
okay. I'm sorry?
I think there's a window with all our faces in front of your presentation.
Google.
Okay. Yeah. Whoops. Sorry about that. How do I get rid of that? Yeah, let's see here. Yeah, I'm not sure what to do there. All right, can I hide this? Okay, yeah, I'm sorry about that. Yeah, I'm not sure what to do about that.
It's better.
Better, yes.
You should be able to click the X button. It won't exit you out of the meeting. It will just close.
Oh, I clicked this one? Okay. Okay. Great. Okay. Thank you. Wasn't daring enough. All right. Sorry about that. All right. Well, thanks. Sorry I can't be there in person, but thanks so much for giving us a lot to speak. This is work that I've done with Ben Stevens and Jun Guo and Adam Harrington. So the question here is, sometimes we want to prioritize the solution in a particular region of the globe. So there, for instance, we might want to make sure we get a good answer over the continental United States because we live there. Or we might want to get a good answer over the eastern equatorial Pacific because we care about the underlying ocean temperature. So let's say we want to do some tuning and we want to prioritize a region. Well, we can do that by weighting the region more strongly. And we know that that's going to degrade the overall root mean square error over the globe because other regions are going to degrade. But the question is, how great is this cost? And does it depend on which region we're prioritizing? So to explore this question of regional weighting, we'll use a semi-automated tuner called QuadTune. So QuadTune divides the globe into 20 degree by 20 degree regions. And normally QuadTune will weight the regions by their areal extent. And we're going to call that equal weighting. But QuadTune also allows the user to boost a weight individually in a specific region by whatever factor the user wants. So QuadTune uses a simple quadratic emulator of the parameter dependence, and it ignores interactions between the parameters. So it's sort of a simple-minded tuner. So let's say we just do an equally weighted tuning of current version of CESM. This is the kind of thing we find. So this is the change in the loss function. So green here means the loss function is decreasing, which means better. So green means an improvement, and purple regions mean a degradation. So we see we have improvements, say, over the Indian Ocean and over Somalia, but then a degradation over the eastern equatorial Pacific. Okay, but the question here is, let's suppose we decide that we want to prioritize the continental United States, or CONUS. Then what happens? Well, when we do that, what we find is we still get some improvements, but there's some degradation, but not too bad. So if you compare the purple regions here, the regions of worse results, it's a little bit worse, but not too bad. But now let's say we decide we want to prioritize equatorial eastern Pacific right here, this magenta box. Then suddenly it gets worse. We have this ugly purple bruised area, which we don't like. And the question of this talk is, why is this? Why would we be able to tune for CONUS more easily than we can tune for Eastern Equatorial Pacific? Or why are the side effects less damaging for CONUS is the question. Okay, so we'll present some tuning runs based on the following configuration. Use the recent tag of proto-CESM3, so something hopefully close to CESM3, namely alpha 07G. We're doing 13-year coupled ocean atmosphere runs, so B-case runs. And when we tune, we're attempting to match observations in both long-wave cloud forcing and short-wave cloud forcing. And there's a bunch of parameters that were recommended to us by Adam for microphysics, Zhang McFarlane, and club turbulence. Okay, so just when we run this tag of CESM, what do we find? Well, in the long-wave cloud forcing, what we find are two particularly strong biases. One is over the eastern Indian Ocean here. So it's essentially a lack of convection. So the long-wave cloud forcing is underpredicted there. But then over Somalia, the blue box, then the convection is overdone, and so the long-wave cloud forcing is too strong. Now, let's say we do some equal weighted tuning. So this shows just what I showed before, just a different color scale, but this is basically the over-prediction in Somalia, under-prediction in Indian Ocean. And then if we tune using QuadTune and a bunch of these parameters here, We find some mitigation here of these biases, not perfect. Somalia gets a little bit better, Indian Ocean gets better, but equatorial Eastern Pacific gets worse. And then we can see what's happening here is that the Indian Ocean gets better because of this parameter W sub I. So basically what it's saying is Indian Ocean, it's way too weak at the beginning. That's the vertical black line. But through tuning, it gets better. It gets closer to this zero bias line, which is what we want, where we want to be. And why is that? Well, this gives the contributions to the different parameters, and W sub I is a big one there. And Somalia gets better, mainly because of this VTRMI parameter. But the Eastern Equatorial Pacific gets worse, again, because of this W sub I parameter. So that's what happens. And the key point is the tuner is going after these large biases in the Indian Ocean and Somalia. And so now we want to know which parameters are contributing to this. Well, we saw that here in this bar chart. It's W sub I and VTRMI. W sub I is basically a scale factor on subgrid vertical velocity. So an increase in W sub I will boost the number of ice crystals. So it can be thought of as sort of a source of ice processes. And VTRMI boosts the fall speed of cloud ice. So it can be thought of as kind of a sink of ice processes. And so what's happening in the model, what seems to be happening is this is sort of the sensitivity to W sub I. And what the model is doing is boosting long wave cloud forcing by boosting W sub I. It boosts it in the Indian Ocean, which we want, but then unfortunately it also boosts it in the Eastern Equatorial Pacific, which we don't want. And then the VTRMI, that's damping the long wave cloud forcing in Somalia, but then it's also slightly boosting in the Eastern Equatorial Pacific, which we don't want. So it's the conjunction of these two parameters, which together probably don't change ice too much, but they shift the pattern in a way that QuadTune likes because it's ameliorating this bias in the Indian Ocean. Okay, so now let's say instead of equally weighting the regions, let's say we just overweight CONUS by a factor of 10. So we're going to take this box and increase the weighting by a factor of 10. And then what happens? Well, okay, in this case, we're just doing equally weighted. This is now shortwave cloud forcing. And then what we see is some improvements here, but we also see some degradations over CONUS and here. So here, Indian Ocean is improved by W sub I, Somalia is improved, CONUS is degraded. Now, if we upweight CONUS by a factor of 10, then CONUS is suddenly improved. It's green instead of purple. So that's good. That's kind of expected. You can see CONUS is improved largely because of DCS. But some of these other improvements aren't as great anymore. So Somalia, for instance, really isn't improving at all. But there are only relatively minor degradations in long wave cloud forcing. So this is what we saw before, all regions equally weighted. Here is CONUS upweighted. And you can see that, yes, W sub I now has been diminished. That was helping us a lot in the Indian Ocean. But somehow magically DCS is coming to the rescue here and helping us there. CONUS, remarkably, which is what we're weighting, actually gets worse. Before it was brought back almost to zero, and now it's brought back too far. It's actually got the opposite bias. But that's kind of an interesting thing. That's outweighed by the shortwave cloud forcing. Shortwave cloud forcing shows a big improvement, and that outweighs this longwave cloud forcing degradation. In any case, the key point is there's only minor degradations in the long wave cloud forcing, and even the shortwave cloud forcing isn't too bad. Now let's say we try and upweight the Eastern Equatorial Pacific. So now we're looking at long wave cloud forcing. This is what we saw before. That's the equal weighting. On this side, we're looking at when we upweight this region here, the magenta box, by a factor of 10. And then suddenly you see the W sub I, its contribution is gone entirely. So basically that parameter has been scaled back. Why is that? Well, because the Eastern Equatorial Pacific was degraded by our boost in W sub I. So then the tuner says, well, now we're prioritizing Eastern Equatorial Pacific. So now we got to dial back W sub I. And so that does help a little bit for Eastern Equatorial Pacific, but then we lose our gains in the Indian Ocean. We also lose our gains in Somalia because VTRMI has been shut down. Before it was helping us, now it's just not there. And so then we get these big degradations. And then shortwave cloud forcing, that has an interesting also trade-off here. This again is equally weighted. We've seen that before. Now we upweight this region here, the magenta box, and then yes, we do improve Eastern Equatorial Pacific, but how do we improve it? We improve it by increasing C8, which is a club parameter, and brings it almost back to 0, which is great, but that wrecks the Southern Hemisphere stratocumulus. So right here, this box is destroyed here, again by that same parameter, C8. So one thing we notice here is that this Eastern Equatorial shows a lot more sensitivity to parameters. You can see this is sort of a wide range here. Like there's an ability to move this bias, whereas CONUS here is showing much narrower bands, which means CONUS is sort of a stubborn bias. So basically, the main thing that's happening is before with equal weighting, we had this nice confluence of W sub I and VTRMI. W sub I was improving Indian Ocean, VTRMI was improving Somalia, and now that's all been thrown into reverse when we try and weight the Eastern Equatorial Pacific, because the problem was this W sub I was boosting Eastern Equatorial Pacific, and now we've decided we don't want that. So all the gains we got here are actually reversed, and then that's the problem. So one way to think about this on a more general level, and to be totally honest, I haven't thought this through completely, but the way I'm thinking about it currently is with an analogy to sort of linear regression. So basically what we imagine is we plot the sensitivity of a region. So each dot here represents one of the 20 by 20 degree regions over the globe. And each of those regions will have a certain overall sensitivity to the parameters. And we plot that versus bias on the vertical axis. So that's how strong the bias is, whether it's positive or negative. And when we have an untuned model, well, then our parameter value is 0. So it's like having a 0 slope on our line. And in this problem, we don't have any intercept. The intercept is always 0. So all we can adjust is the slope of the line. And when we tune, what we're doing is adjusting that slope. And we're trying to bring the line from just a horizontal line at 0 back to a line that passes through the points. So, we can try and do that, and we've done that. But now let's suppose we say we want to upweight the CONUS point, and that point lies here. Well, what's going to happen? Well, the line is going to want to be drawn down towards CONUS, right? Because that line is suddenly upweighted. But there are going to be some problems. First of all, CONUS isn't particularly sensitive. It's close to the y-axis here. And so basically the line can't be brought down too much without degrading the other points overly. And so basically the tuner is going to kind of ignore these points that are close to the y-axis that have low sensitivity. And the other thing is CONUS really isn't too far from these other points. So basically what's going to happen is the model won't do too much. But now let's say we have Eastern Equatorial Pacific. As we saw, that's a much more sensitive region. We could see that before because we could see how wide these bands are, how much these parameters are moving that region as compared to CONUS. And furthermore, the bias is the opposite, at least the opposite as it is in the Indian Ocean. So now, if we try and weight that, what's going to happen is this line is going to be pulled way down because it has high sensitivity. It has a lot of leverage, as the statisticians would say. It's way out from the y-axis. And so, yeah, we can improve that region much more than we could say improve CONUS, which is a more stubborn bias. But by that very act of improving the Eastern Equatorial Pacific, we degrade these other regions a whole lot more. So basically, it's just saying that we can't win. We have these regions where there's model structural error. They're not grouped together with the other regions. We can weight them if we want. And I'm not saying we shouldn't specially weight certain regions. There are some regions that are more important than others. But if we do that, there will always be this inevitable cost of degrading other regions. And even if we can improve the region we want to improve, well, then that just means the cost is greater in terms of degradation of the other regions. So the conclusions are, in equal weighted tuning will tend to prioritize the most sensitive, largest biases. Here in this run, it was Indian Ocean and Somalia. If we prioritize a regional bias, the overall accuracy is going to degrade. Well, that's We knew that beforehand. But the degree of degradation depends partly on the degree of consistency, how close the point is to the other points. In other words, how big the error is. But it also depends on the leverage. In other words, the sensitivity of that region to the to the tuning parameters. So thanks. That's all I have.
Are there any questions in the room?
Yeah, Vince, let's talk. Wondering whether you've
Thanks.
thought about or examined how these kind of like compensations occur. Is it purely a column physics setting, or do you believe that some regions are more susceptible to non-local circulations than others that are kind of a more indirect impact?
Yeah, I didn't show that really, but yes, you can look at omega and you can see that in the CESM simulations, the vertical velocity, the substance velocity is quite far off in some of these regions like Indian Ocean and Somalia. And you can see that by tuning W sub I, omega comes closer to what the reanalysis say. I know reanalysis, it's omega isn't perhaps too trustworthy, but still, if we assume it has the right sign, then it comes closer. So you can see that there's definitely a compensation, sort of a circulation difference between whether we're weighting Indian Ocean and we actually have convection there, and Somalia. There's a trade-off just in the circulation itself.
Any questions online? Thanks, Vince. I had a question. What you're calling structural errors seem to be related to biases and like where there's deep convection in the model, there might not be deep convection in reality. I'm wondering if you've thought about maybe applying this technique to something like Patrick's nudged or spectral nudging, a simulation where the large scale is being constrained, but the small scales kind of and the parameterizations get to kind of act up in whatever way they want.
Yeah, I haven't tried that, but that's a good idea. Yeah. I mean, one thing I do notice in the Indian, so I don't think that W sub I is probably really the right parameter if we want more convection over the Indian Ocean. I'm guessing it has something to do with the surface fluxes. That's just a guess. But you can see that the winds are sort of under-predicted in the Indian Ocean in this particular version of the model. And so, yeah, if we could nudge the winds back, that would probably tell us something interesting.
Right. Well, thanks, Vince. If
Thank you.
you have a talk by Proclamation, is it loaded up?
Hello, everyone. So in this talk, I'll present our recent work on optimizing objective model calibration approaches using single column models with a focus on parameter identifiability, equifinality, and uncertainty or calibration. I am Papu Pal, a PhD candidate from Department of Climate, Meteorology and Atmospheric Sciences, University of Illinois, and I work with Christian Pestisescu, assistant professor of the same department. Before jumping to today's research talk, I want to quickly go through the outline first. At first, I'll talk about what is the parameter uncertainty and why it is important and why it limits the model skill. And then I'll go through the motivation, why we are doing this work. And then I'll talk about the unique part of our effort. And then I'll show some results and then a summary. So let's jump in. So in the Earth system, there's like a lot of physical processes like condensation, deposition, vaporization. And due to the computational constraint, these things are represented through parameterization. And there is different parameterization like microphysics, turbulence, convection, aerosol, etc. And due to this parameterization, it creates some sort of uncertainty. One uncertainty is like a structural one, where the different parameterization scheme give different subscale processes. Say, for example, in this plot by Duffy et al. So if you see here in the tropical anvil cloud and in the yellow dots from the CMIP model, so different models gives different cloud feedback, and this spread is the structural uncertainty. And there is another kind of uncertainty called the parametric uncertainty due to the value of those parameters. And if you see again the tropical anvil cloud, the blue dots PP, the model CAM6 is run with the same condition, only the change is the parameter, and the spread is due to the value of these parameters. And if you see the spread, both of the spread, so the parametric uncertainty is as important as the structural uncertainty of the model. And in our work, we are only considering the parametric uncertainty, not the structural one. And there is a lot of efforts ongoing here in NCAR. There is a work by 2D. It is not focused on the parameter calibration, but they also mention people can use PP to calibrate the model. And there is also in DOE E3SM model, they also use calibration. And more recently, there is like a machine learning approach to calibrate NASA KISS model. All this model, all this calibration algorithm needs a lot of model run. Even though the machine learning approach, you need to train your emulator to tune the model. So all this thing needs like a lot of 3D model simulation, which is very costly. So what is the unique part of our effort? We are using the single column atmospheric model SCAM, which is basically a column of CAM6. And we are considering 11 microphysics, 9 aerosol, and 11 convection parameter. Within the value of each parameter, we use Latin hypercube sampling to create like 100 parameter ensemble and 500. So we are creating two different ensemble size because we want to see whether there is any impact on the ensemble size in calibration. And then we ran the single column model on Southern Great Plains, SGP. And we, even though SCAM is pretty cheap, you can run a single year within few seconds, but still we are using the Gaussian processor emulation because in the later part of the talk, I'll show you, we use the Hamiltonian Monte Carlo parameter distribution to constrain the parameter. This is a probabilistic approach, and it needs tens of thousand likelihood evaluation. So if we want to SCAM, if we want to run SCAM directly at every step, it would be very inefficient. That's why we use the emulation. Another thing we are considering the perfect model test. What I mean by perfect model test. This is in the perfect model test, there is like no real observation we are using.
There is a microphone here. I wonder if this microphone is on, and then it's.
Yeah. Okay. So.
Sorry?
You can use that mic as well if you want.
Okay.
So as I mentioned that I am not using any real observation. We are creating the synthetic observation by running a SCAM. So the beauty of this perfect model test is we know the true parameter behind this synthetic observation. So when we will compare all of our PPs to the synthetic observation and retrieve the parameter, we can compare whether we are getting the right parameter retrieved or not. And we are doing this by two methods. One is like traditional calibration where the RMSE-based observation fitting. And the next one is like Gaussian processor-enabled Hamiltonian Monte Carlo, which is like a Bayesian approach. So let's jump into the results. Here we are seeing the vertical cloud fraction. X-axis is the cloud fraction and y-axis is the pressure. And here the pink spread is the scan ensemble. And the gray spread is the emulated ensemble. And the green line you are seeing, this is our observation, synthetic observation. And the best match SCAM ensemble member is dash black line. In that case, RMS is 0.01. So the black dash line is pretty close to our synthetic observation. And also there is a best case in case of emulation, which is solid black line. That is, in that case, again, the RMS is 0.01. So as we closely match with the synthetic observation, so the parameter behind these two best cases should be the parameter of the synthetic observation, right? Let's see what happened in the parameter space. So this is the normalized parameter error. The x-axis is the normalized RMSE in parameter, and y-axis is the different parameter names. Here in colored, microphysics is in black, aerosol in green, and convection parameters are in teal. The true set of parameter is the red dots. If you see the best case in case of cloud, we show earlier slide, the parameter on the best case here is the gray dots. You see the best case match with the observation, but the parameter, most of the parameter are really away from the true ones. So by RMSE fitting, we can match the observation, but maybe for some wrong result, the parameter is not retrieved well in RMSE. And why it's happening? Maybe this is equifinality. Even, in fact, we did this test for different ensemble size. What's happened there? So as I show here, the left upper panel is for 500 pp, and the right upper panel is for the GP emulated case. And on that case, you can also see that the gray dots are scattered all over. So, and again, for 100 pp, gray dots again scattered all over, and the corresponding emulated case scattered all over. So when you change the ensemble size, you are retrieve some different sort of parameter. And this is happening due to the equifinality of the model, where model can give you the same result for different parameter combination. So this result tells us the ill-post nature of the inverse problem of this parameter retrieval. So we need some sort of other technique to calibrate or retrieve the constrain the parameter. For that, we use the Hamiltonian Monte Carlo, which is again, I said like it's like a Bayesian approach. And this here we are seeing the normalized posterior distribution. X-axis is again all the parameter name, and y-axis are the parameter values. Here, all the boxes are interquartile range, 25th to 75 percentile, and the parameters are sorted like lowest IQR in the left and highest IQR in the right. And red horizontal lines here are the true parameter, and yellow horizontal lines are the median of each posterior distribution. Here you can see in the left part of this plot, we retrieve and we constrained parameter really well, but if you take a look on the right side, we are not retrieved that well. And this is for cloud, by the way. We then again check for some other variables like liquid water path, relative humidity, and restome. And again, you can see the left part of the plot, we retrieve really well. We constrain the parameter really well, but right side is not retrieving that much. But one good thing is like consistency. I mean, like same sort of parameter, we are constraining using the Hamiltonian process, same sort of parameters. So this is consistent, whereas the RMSE-based method, every time you get like different set of parameter. So why that is happening? Why left side we can retrieve, but not the right one? Because the sensitivity matters. Here you're seeing the lower panel is actually the regression-based sensitivity of the parameters. And all the darkest color here are most sensitive parameter, and the lightest color on the right side is not that sensitive. So as the parameter of the left side are so sensitive, that's why we are retrieve those set of parameter, not that. And this is as expected. We did this for 100 pp case too, and get the exactly same set of result. But in case of 500 pp, we get like more correct constraint. So the larger you have, the larger member of ensemble give you the more constraining set in this case. And here, so the summary is like the traditional observation fitting cannot retrieve the true one. And the second, we showed that the probabilistic calibration using Hamiltonian Monte Carlo is more robust and informative because it identifies the sensitive parameter and quantifies uncertainty through posterior distribution and provides physically meaningful constraint rather than arbitrary points like RMSE. And this is across, this is consistent across variable and ensemble size, which is very important. So I can say like SCAM is very efficient tool for training the GCM, but all these results we are showing here for only single location in Southern Great Plains. So in future, we have like a plan to run the SCAM on some other location like tropical West Pacific, northern slope of Alaska, like all the ARM sites to see how these things go. And finally, we aim to test this constraint parameter in full 3D model to see how SCAM-derived calibration translate to large-scale models. And again, this project is very new. We just started the work, so we really welcome any sort of collaboration and testing these methods in any physics configuration or SCAM setups. That's it. Thank you.
Are there any questions in the room?
I'll just make a comment that like we've seen several, parameter estimation talks using machine learning, and they're all pointing to the same 5 parameters or so as being the most sensitive. VT, yeah, exactly. Everything to the left there, W sub I scale, TKAD, DCS, VTRMI. I mean, that's just clearly those are the most sensitive parameters in our model.
Yeah.
I guess I didn't understand exactly what you were doing. I suppose perhaps you could explain the perfect model approach. I'm not really.
Okay, so the perfect model test is here like, so when we calibrate the model, use the observation, and we try to match our model result with the observation. And then we say, okay, this is our true parameter, or this is our correct parameter. But we don't know whether this is correct. So in our perfect model test, we didn't use any kind of real observation. We synthetically generate by running SCAM. So we know the parameter behind that, that synthetic observation. And then we calibrate using PP and retrieve the parameter. And then we compare, okay, this is our retrieve parameter, this is our true, whether it's match or not. And this is the perfect model test.
So the perfect model.
Perfect model means like we are using for generating the observation, we are running SCAM, and for PP we are running SCAM. So this is like a same model, same structure, everything is same. So
just to clarify, when you evaluate those PPE members, are you looking at one variable, or you can have many variables?
So like we have like multiple variable like cloud, liquid water path, relative humidity, restore, and we also have the LWCF and SWCF, but I didn't show those things here. So we have, and we have like temperature, we have like total 7 variables.
Is it possible that if you use multiple variables to evaluate, then you can reduce the equifinality problem?
So for that here you see the gray dots are for cloud-based case, but the pink rectangles, that is for liquid waterfall. And you can see the pink rectangles are also scattered all over the parameter space, and most of them are away from the true one. So this is again tells us the equifinality in the traditional RMSE-based observation fitting.
Are you using those variables together?
Oh, so you said combined. So yeah, there's like a cyan color on a mean RMSE combined case, and those are also scattered all over. Yeah, we did that, but same.
If there are no more questions, thank you, Papu, again. And we'll go to the next final talk of the session with Todd.
All right. Yeah, it's working. Hi, everyone. So I'm Todd. I'm on postdoc here in CGE. I'm in the climate analysis section. And my talk today is about leveraging observations and model experiments to kind of develop constraints on tropical convection in CAM. So it's going to be kind of a short talk. I'm just kind of giving a survey of some recent results. Yeah, let's hop right into it. So this is part of the Inform project, by the way, that me, Christina, Ryan Petnod, and John Truesdale back there, we're all working on. It's kind of a way to use novel data sets that haven't really been used to constrain models before, to kind of come up with better representation of clouds. So our goal here is to develop a suite of model diagnostics. My kind of role in this project is just improving the tropical convection in CAM. And the way I do that is just I combine like simple theory, convective quasi-equilibrium, and that kind of stuff, little research models like toy models and a variety of observational products just to kind of construct these constraints. So I'm just going to give an outline. So I'm going to talk about a diagnostic that I've used extensively through my PhD. It's called the precipitation pickup diagnostic. It just kind of shows the transition of convection and the sensitivity of the environment in the model to convection. Then I'm going to get into a bulk plume framework of buoyancy and just kind of go through the importance of mixing. And we're going to develop a new diagnostic for convective sensitivity in models. And so the bulk plume framework is going to be a little bit of background. So if you have extensive knowledge in tropical meteorology, then I'm sorry, you're going to have a quick review. Then we're going to get into CAM6 PP experiments. And yeah, I'm just going to talk about which parameters are most important for this convective sensitivity and which ones can use improvement. So this is a precipitation pickup. On the right here, this is observations from the Nauru atmospheric radiation measurement field campaign site. The precipitation is averaged every 3 hours, and that's on the y-axis. So that's conditional average precipitation on calm water vapor, which is the x-axis. So it's a relationship between calm water vapor and precipitation, where you see that the precipitation kind of lies flat along low values of calm water vapor, and all of a sudden kind of takes off when it reaches some critical value. And it's identified on short and daily timescales over both tropical land and ocean. So what I mean by the pickup is I'm kind of talking about this right here, this kind of takeoff. It really represents the transition to deep convection. And here you can just kind of fit a line through it, and you can come up with an estimation of like a critical value. So you can say, okay, when you hit 60 millimeters of calm water vapor, you kind of expect your precipitation rate to kind of increase rapidly with every excursion above that. And so just for reference, if you aren't familiar with the Nauru ARM site, it's 13 years of data. Here just average over 3 hours. So it's very extensive. There's a lot of data there to work with. So the pickup is also measure the model sensitivity. So as your critical value gets higher, or your pickup kind of lies later down the line, here I'm showing column relative humidity this time, you start to get an idea that, okay, your model's a little too, it's insufficient, it has insufficient sensitivity to moisture. And this is mostly due to entrainment. So you're just saying it has too much mixing going on, it takes too much column relative humidity for the model to actually kind of start convecting. And so here in the figure, I have the same figure I just showed before. This is also at Nauru, and what I've done is I've taken an ensemble of CMIP6 models, and I've kind of calculated this pickup condition on column relative humidity, and I put them in order on the in the legend according to what their critical value is. So you start to kind of see some patterns. The MPI models, for example, kind of pick up much earlier, whereas NASA GISS picks up pretty late. The NORI-ESM models pick up kind of close to observations. And when I'm talking about observations, I mean kind of these black ones here. So I have the ARM data kind of matched up with TRMM 3B42 precipitation. I also have AIR5 here just to kind of give an additional baseline. So the model's actually doing pretty good. Some earlier work kind of doing the same diagnostic or metric. And Rushdie et al. 2018 found that models in the CMAP5 generation were actually picking up much earlier. So now now observations kind of lie in the middle of the pack. So there's still some biases that are persistent. So I'm going to we want to find out why these models are picking up early, why they're picking up late. I mentioned mixing earlier, right? So we want to look into that as kind of an important parameter. But here I'm just going to kind of talk about a little bit of the bulk plume physics. A lot of models kind of rely on this bulk plume kind of framework for their convection schemes. So here we have, this is very introductory. On the left, I have like just the lab straight temperature with height, and then I can convert that to equivalent potential temperature here. And I've just plotted the condensation level and level of free convection according to what that plot is. Basically, I have theta E plotted here on the right, and it conserves theta E is a conserved variable with respect to adiabatic moisture transformations between water phases. So it's very similar to potential temperature, but with effects of moisture taken into account. And so when we look at buoyancy, the reason it's a lot, you can come up with some diagnostics with these kind of conserved variables, which is why I like to use them. Buoyancy in the theta E kind of space is represented by this difference in theta E, fractional difference in theta E with some kappa factor on the bottom, which is just a scaling factor. But you can see that it actually is a lot easier to kind of just have an analytical framework behind how bulk plumes work just by taking any parcel or any theta E from any level and just lifting it up and conserving it. And so if we want to kind of like get into mixing, so the mixing with theta E is linear. Which means that as you start to raise your parcel up, it's going to mix the environmental theta E, which is this dotted gray line here. So if we like just take some mixing into account, you'll see the line shifts from no mixing here to what a mixing case looks like. And what you notice is that mixing has a large impact on the buoyancy of plumes. So if the plume weren't to mix at all, this case would be buoyant. And if the plume were to mix, it would be not buoyant in this case because it lies to the left of the theta ES of the environment, which is the black line. And this is also, sorry, I forgot to mention, this is also from the ARM-BE product, or the ARM product, but this is their best estimate product, so it also includes the vertical profiles. And now we can kind of take a simple two-layer approach. So from the plume equation, you just have the plume changes as it rises, the theta E, according to the difference between it and the environment multiplied by some mixing rate. So you're basically just kind of diluting the parcel as it rises. And we can start from the boundary layer and just raise it up, and it's going to mix with this kind of red subsaturated region here. So the red is called subsaturation. It's kind of like a moisture deficit, and it's really similar to relative humidity. And we kind of get this, we can estimate what the plume value is at the top of the lower free troposphere, let's say 600 hectopascals, just with this more or less linear approximation to it. So it's just the boundary layer value plus the subsaturation times some dilution. And so if you kind of look at buoyancy, it scales very similar to this equation here for the plume theta E. You can just kind of say, okay, buoyancy is proportional to the difference in the theta ES of the plume and the environment. You just subtract the theta ES of the lower free troposphere from that approximation there. And you kind of get the idea that, or it recasts buoyancy as a weighting between subsaturation and instability. So I'm going to get into the astral diagnostic now that we've kind of gone through a little bit of background. Okay, so here in this figure, I have AIR5 precipitation, conditional average precipitation. So you remember that pickup we looked at earlier? This is now in 2 dimensions. So the colored contours here, the filled in contours, are the precipitation value conditioned on the subsaturation on the x-axis, and the instability, which is just the boundary layer value, and the lower troposphere temperature on the y-axis. So we're trying to find out what the weighting is between the two. And the way we're doing so is we're saying, okay, let's say precipitation, the strength of the precipitation is a proxy for buoyancy. So the gradient's going to point in the direction in which buoyancy increases. We're going to say it's approximately the same way in which precipitation increases. So now we're just going to kind of find the best estimate for finding out which direction buoyancy increases. So I can do something like, okay, how about we take the gradient field and then I just weight it by the probability of precipitation, these light red contours here. So here in this figure, you see the tropical Western Pacific for Area 5. The black arrows kind of just point in the way of the gradient, scaled by the probability according to the conditional average precipitation here. Everyone get that? Great. And this is this actual math for it. It's geometry. But basically, we're just trying to describe how well can the gradient of this field here be described by one direction. That's all this is. So we're just going to solve for which direction is highest correlated with the gradient precipitation increase. And so I'm going to start doing this. I'm going to apply this kind of framework to the diagnostic. We just saw it for an Area 5 case to some CAM6 PPE experiments. So these kind of set of PPE experiments were mentioned earlier, but it's 262 CAM6 runs with perturbed parameters. They're all kind of randomly perturbed in each run, so you don't have like a control case and perturb just one. It's kind of all randomly sampled. And we have monthly output for 3 years, so we're going to be doing more of a climatological analysis, and we're going over a large spatial domain. So this is just in the tropical West Pacific. And so we can do that analysis here, is the same kind of plot I showed earlier, but for different CAM6 runs. On the left here, I have an entrainment rate that's closer to 0, which means that it has a much smaller entrainment. So you can kind of see that the arrows all point up because they're instability dominated. They don't really care what's going on in the lower free troposphere. They're not mixing. The convection is really just tethered to the boundary layer. And on the right here, I have a run that has a very high entrainment rate. And you can kind of see it just moves, the gradient moves in the direction of subsaturation. So it's really dependent on how moist the lower free troposphere is. And each run, so we have 262 runs. So each run gives a measure. Here I'm using angles just to make the analysis a little more readable. That measures the sensitivity of convection to either the moisture in the LFT or the instability from the surface in the lower free troposphere. And now we're just going to find which parameters are leading this kind of gradient field to kind of rotate and move about. So I can run a correlation analysis. Sorry, I think when I converted it to PowerPoint, I might have put some spaces in there. But these are the top 5 parameters with the highest correlation that kind of move that gradient field the most. So number 1 is the Cape limit. Number 2 is entrainment. Number 3 is, I think, evaporation efficiency. Or maybe and then sorry, I have these all listed on the same slide. It's really hard to memorize variables, exactly what they do. But you can kind of see it's dominated really by the deep convective ZM scheme in CAM, which makes sense for looking at convection in the tropics. And then there also is a club variable that's important too. So this is a lot. I'm just going to read it one by one. So here I have that actual correlation we just saw here. And I'm kind of showing which way, as you perturb that variable, if you increase it, what it does to the actual sensitivity. So if the line's trending down, it means that it's moving it more towards subsaturation. And if the line has a positive slope, it means it's making your convection more dependent on instability. So the Cape limit's the most important one that we found. Basically, the entraining Cape requires more moisture to attain high values of Cape to actually convect. Number 2, we have deep convective scheme here. Less entrainment means that you need less moisture to stay buoyant. So what it does is it's moving it towards more of an instability dominated regime. Number 3, we have higher convective evaporation efficiency, means more LFT moisture is needed to correct kind of a leaky sort of convection. It's just evaporating more moisture, so it needs to retain more, or needs more moisture in the LFT to actually sustain convection. Auto conversion over here, over ocean, that's what this variable is. More condensate is giving, and this is all kind of what I came up with, so if anyone has any ideas of what's actually leading the sensitivity to change, please let me know, because it's kind of hard to untangle it. But more condensate's giving more evaporative cooling in a moisture lower free troposphere. This one I think is more of a, not so much causation, but more of like a result of that convection happening with this lower variable, or increasing this variable or the parameter. And then the club parameter, the more moisture dissipation you have, The less subgrid moisture variability, which means convection just really depends more strongly on the grid mean subsaturation. So it's moving it more towards a subsaturation dominated convection. And then we can kind of actually separate this to sensitivity by parameter class. So you can kind of see that in tropical convection is of course dominated by the convective parameters, secondarily by club, and then there is a small contribution by microphysics and some of the others. And this is just a box and whisker plot, the built-in Matplotlib one. So it's interquartile ranges, and then the orange line is the median. And so the idea of future work is I want to use scam runs to kind of zoom in on the parameter classes, find out which parameters maybe matter more for precipitation extremes. And I also want to do more of a time-dependent analysis too. And really kind of developing these diagnostics to improve the model, we have to ask ourselves, like, what variability do we wish to capture, and how do we going to build constraints for these parameters moving forward? And that's it.
Any questions?
So once you sort of identify the 5 most sensitive parameters, it would make sense to just do like a controlled perturb parameter for each of those to get like a better idea of like what happens when you increase and decrease those parameters instead of just going off of ensemble, because the other parameters being changed is kind of like hidden in the rest of the perturb parameters, right?
Yeah, no, totally. And that's the idea. It's kind of disentangling in, and then now we have these ones figured out. So instead of doing the full runs, we'll probably just do scan runs. Just to kind of get that idea. Yeah, they know exactly. Yeah.
Do you feel that could this inform something of the kind of, let's just say, the entrainment rate single value? It's just not the way to do it. It has some difference in the vertical. Do you think this analysis could reveal that kind of single parameter, error, if you like? I don't quite know how to phrase it, but like, such that you should not be using a single value for this.
Yeah, I think it's possible. I mean, a lot of the work is with conditional averages. So of course you can look at how that field changes across different precipitation rates. You can kind of see maybe the entrainment rate, if you have a good idea of how to estimate it, how that changes. So it definitely could, and I think that's what I want to look at with the scam runs. An important part too is that we also need another constraint for kind of coming up with what we want these values to be. So the way I'm looking at that is, for example, we can look at like observations of environment during where we know there's more entrainment, or if we have measurements of mass flux, and then we can kind of come up with, a more dependent entrainment parameter that isn't just one single value. So when I'm going towards that, I'm looking at like the tropical environment, and I want, maybe the profiles of theta E and theta ES to kind of be more similar to observations when we kind of construct those.
Thanks, Todd. I think, I don't think there are, I don't see questions online. Are there any?
Yeah, the C2RT parameter has shown up, I think, in Trudy also in her PPE noted that one. And I don't quite understand it. So can you go back to the slide that explains your theory?
Yeah, this is a theory.
So yeah, this thing controls the dissipation rate of the R2 prime squared, so the moisture variance. And so less subgrid moisture variability, leading convection depend more strongly on the grid mean subsaturation. Flesh that out for me a little bit.
So the way, and please correct me if anyone knows a lot about this club, because it's, so when you increase that parameter, right, you're kind of increasing the dissipation rate, so you're decreasing the subgrid variability of moisture, which leads to the subgrid convection. Is that correct?
Yeah, the convection from club is really, I would say it would impact the amount of moisture transport in the boundary layer.
Okay.
Because club is kind of more of boundary layer and shallow skiing.
I see.
So there's no direct impact from this parameter on ZM.
Well, I'm thinking ZM is very sensitive to the amount of moisture in the boundary layer.
Mm-hmm.
So I'm wondering if it's just like it's affecting the amount of moisture that then increases CAPE, which is what ZM sees.
Yeah, no, it could. I mean, this is just kind of agnostic to, these are conditional precipitation fields that they're not
they don't know what the parameter values are, like the 2D means where I'm getting these from. They're kind of just like off these. And I just look for the correlations there. So I thought, yeah, the way I looked at this was like the moisture dissipation rate. If you increase it, you're having less, variability in the moisture. So you're kind of just flattening out that PDF that operates in the club to just be kind of whatever the mean in the grid is.
Yeah.
So it's more tethered to like, hey, you need your moisture to kind of go up a lot because we just care about the mean. We don't really care about whatever this variance is in the box.
Gotcha.
But it is kind of hard to, if you have any other ideas on the diagram, because
I have to think about
it took me a while to think about this one.
So, but the magnitude of the arrow, I'm wondering if this is the magnitude of the arrow is not represented in these plots. It's just the direction.
Yeah, the slope. So the slope, if it's smaller, then once it goes to zero, it's just the parameters don't have an effect. Like it's just random. It's not really affecting sensitivity. So yeah, the slope of these really does matter. So the top 5 should have the highest. It should be kind of in order of the absolute magnitude of the slope that ends there. So you'll get to a point, where it's 0, and then just means you can perturb that parameter as much as you want. It doesn't really affect the sensitivity of convection.
Okay, I think I misspoke when I said magnitude. I'm wondering, what is each one of these dots?
Oh, that's a run. So on the x-axis, we have the parameter standard deviation, kind of the perturbation. And then on the y, we have the sensitivity. So that is the angle of this arrow, the red arrow.
Averaged over all of the tropics? Or
over tropical West Pacific. So these maps, these are conditional average 2 dimensions, and all these values are just from tropical West Pacific points.
Gotcha.
So what I do, so we get for each run, 262 runs, you get one value, one angle that describes whether it's depends more on CAPE as the left axis or instability, and then on the right, if it depends on more relative humidity or subsaturation. So then this plot here is those 262 runs plotted as that sensitivity measured by the angle versus the standard deviation of that parameter in the PBE.
I think the question is only the angle of the red arrow is represented in these plots, right? Not the magnitude of the arrows.
Oh yeah, only the angle, not the magnitude.
Yeah, that was the question. Thank you.
Okay, thank you.
And I do wonder, speaking of magnitude, I'm wondering if the magnitude of the precipitation is significantly different in any of these dots, or if they're kind of all the same and can't impact that.
I think it should be different. It's something I should probably look at.
Yeah, that would be an interesting sensitivity. Again, because the fact that club impacts convective processes in the West Pacific so much is, a bit of a surprise to me.
Yeah.
Thanks very much. Peter had built in a few minutes for wrap up. Suppose we could. I don't know if Peter is still on the line. Do you have any particular suggestions for topics?
Yeah, we have a little bit of time just in case anybody has anything they wanna talk about while we're all here. While you think about that, I'd just like to thank the AV crew that's sitting behind you, behind the glass window. They always do a great job supporting this. And then also for the admin teams, for Kayla and Elizabeth and so on, and doing all the hard work behind the scenes. And also thank you to all of you for giving these really good presentations. In particular, Cecile and Rich, they only submitted one abstract each, but then they got to give one bonus presentation on Monday. So thank you for doing it.
Bonus for who? For us, thank you, Rich.
I will discourage you from submitting abstracts in the future. And if there's anything about the meeting organization or something you want to have done differently, just reach out to me directly. So if nobody has anything they want to raise or talk about, then I think we can end the AMWG meeting for 2026.
Thanks.
Yeah, going once, going twice.
Thanks, Peter.
Thank you.